fire extinguisher hiding behind the bench there. First aiders, I think Dave's pretty awesome. He can probably help us out. He'll give you mouth to mouth whether you want or not.
That's a little tongue in there too.
Hey man, whatever. If you're the savior, you're the hero. Washrooms, there is a actually no, there isn't. There is no longer a washroom in the change room. It's going to be a men's washroom. They're literally demoing it today, walling up the door, punching a new door into the administration wing, and there'll be no longer be a washroom available in the locker room. Yeah. So the washrooms are downstairs beneath us. Head down these stairs, do a loop-de-doo, and there's a washroom right there. And then there's the ones in the shop back here as well. We'll take our breaks at about the regular time, so you guys can get to the gut truck, or we'll give you probably 20 minutes or more, so the guys have to get back to the building too can. We should be done by lunch. We're basically going to just go until we're done, and then you're back to work for the afternoon. At the end of tomorrow, I'll give you the evaluation sheets where you can bullshit your way through how good or bad you think I did, and rate me so I can prove to the people who oversee the course that I actually did it. Otherwise, all the information recorded in the course manual, which is yours. Again, as per yesterday, I cannot reuse these manuals. Now, once your name is assigned to that serial number, they know the powers that be know it's in use, so I can't reuse it, so you're not doing anybody any service if you leave it here. Take it home, set it on fire, roll it up, smoke it, I don't care. Whatever you want to do to get rid of it. Or use it for reference down the road because it's a valuable tool. It is full of good information. And I mean, most of this stuff...
You just use the QR code.
Right?
Then you don't need to do it.
There's that too. Put it in your phone. You'll never have to look at it again. A lot of this stuff, you're not necessarily going to remember it unless you have a kick-ass memory, but it's important. It's kind of knowing what you don't know. At least it gives you a frame of reference to say, hey, I should go look this up. And then you can always look it up. Thanks to the internet, there's a ton of resources out there to find information. But if you don't know you need to look for the information, then you're just going to do things obliviously, and that's when things can go wrong. So after completing the course, you'll understand the principles and practices for safely using slings, rigging hardware, and below-the-hook lifting devices. So in this case, you're giving us a wonderful example of a few bad things that we should never do when it comes to rigging. Anybody see any problems with that?
Well, you should be pulling. Well, you're side pulling lift ties using one sling instead of two.
Yeah, so that's called reeving. So they've used one sling through two holes. So what's going to happen is, yeah, it might lift the thing up, but it's also all the force is going in, and that's going to, not only are these not shouldered, so they're actually not all the way down like they should be, but because of the orientation of them, they're going to try and bend inward under the weight of that object. So there's all kinds of things wrong with that particular example. Should never reeve slings to other slings or other objects. Use two. Well, ideally these should be shouldered down and you'd have two back in the hook and not just the one. Another example of what not to do, that's the end of a sling by the looks of it, and it's literally just caught underneath the bolt. So there's all kinds of things wrong with that. That bolt has sharp edges, it could easily shear it. It's definitely not the way the sling is designed to be used. If anything were to shift, it would fall out. Just not a good practice. Find a better way. If you don't know a better way, stop and ask. When it comes to this stuff, there's very few people who are amazing at all of it. It's always good to bounce ideas off each other and find the best way possible if you're in doubt. So in that case, it would be the left side of the orientation of the hook and lift eye. So it looks like they have a nut underneath the lift eye, which is not a good idea. Looks like one of our chucks though. And then the other one looks like it's a picture from the 1940s. I mean, if you ever get handed something that looks that old, and if you get handed anything in black and white, don't use it. Yeah. Oh, and obviously, they have it literally, the pin on the shackle is through the plate, and then it's not threaded all the way in. So, yeah, people get creative. The old necessity is the mother of invention is true. When it comes to rigging, it's just setting yourself up for disaster. So don't cheat. Do it right. Get the right tool. One thing we are pretty good at here is getting the right tool for the job. If we need to buy something, we'll buy it. Like those things I got you guys there a year ago or so for that heavy lift. It was only $200. Like that, for what it was, that was nothing in the scheme of things to get the right tool for the job instead of half-assing it and risking disaster. So you always get the right thing. This one looks like it's been side pulled pretty badly. It's bent right in half. The latch is right screwed as well, but the bigger problem is it's bent in half. And if you ever get handed wire ropes that look like that, if they're permanently kinked, don't use them. There could be all kinds of things wrong on the inside, and they are susceptible to such things. We're going to learn about how that happens and the proper way to use them. That top one there is kind of what could happen with that reefing at the beginning, that things get pulled at an angle and bent. Looks like it's also got some thread damage going on there as well. And then that one's been rode hard and put away wet. It's probably stretched out. We should never use anything where the threads are showing on the inside because that can cut the slings. Plus it's not fully engaged, so how do we know if it's actually rated? So we're going to see this over and over and over again is kind of the order of operations for how these things get made and put into service. Well, there's OH&S, which is the government, of course, then there's the Society of Engineers, which are all the smart people who do all the math and figure out what things are capable of. The manufacturer then uses the two, OH&S and the mechanical engineers, to decide how their things are going to be used, and to tell you how the things are supposed to be used, and then the employer is going to tell you how they are going to allow you to use it. So that's kind of the order of who's in charge of what. At the end of the day, you're the one using it, so you're responsible for it. If something fails, it's up to you to make the right choices. Rigging Resource Center, as Dave pointed out, there's QR codes and whatnot. If you ever need to look something up when it comes to rigging, this is a hell of a good resource. It's good to keep it, whether it's in your favorites or whatever, who knows. But basically, there's a ton of options out there for finding information that you know you need the info, but you don't know what the info is. You can always look it up. That's just telling you how to use the online thing. It should be pretty straightforward. So 3 types of inspections are required for slings, hardware, and below-the-hook lifting devices. Your initial, so when you first receive it from a vendor, you should be checking it to make sure it's the quality and what it is what you expect to get. Your before each use, at the end of the day, if you're using rigging, you should be checking it before you use it. We've gotten a lot better at putting our rigging away and taking better care of it. We don't just drop it on the floor beside us and drive over it and pile stuff on top of it or drag it across the floor back in the Garrett days. We are pretty good about hanging things up when we're done in housekeeping, but you should still know what condition it's in before you use it. And then quarterly we do periodic inspections. That's only for the below-the-hook lifting devices, magnets, clamps, and chains. And that's just a visual inspection to make sure that it looks copacetic. The people doing it aren't amazingly well trained. They're just guys like you who've had this training. But they do catch some stuff. And basically, if they see anything they don't like, we tag it out and we send it to the experts. It's just a way to avoid having to send every single thing we have to the experts. We have caught issues with chains. We've had chains get bent, kinked. We had the ones in welding there a while back that had actual weld spatter on them, which was a good catch on Clark's part. It proves diligence that you went and found, looked at it close enough to find those little beads of spatter. Shit does happen to this stuff, so it's important we get to know it and take care of it and don't take it for granted. When it comes to regular nylon slings and all that, if you don't like the way they look, give it to your supervisor, tell them you're taking it out of service, then they can buy new ones and they can scrap the old ones. There's really no need to use crappy slings. I think Jacob just got I ordered 20 slings for him recently to replace a whole bunch of his, so we should have ample supply of good slings floating around. For your initial inspections, verify that it is the correct item, make sure it's undamaged from shipping and complies with ASME standards. Frequent inspection before each use, look for any condition that causes doubt, and you're going to see that over and over and over again, and that is the biggest thing in basically everything. If you're in doubt, don't. Stop, ask the question, talk to your supervisor, find me. Odds are I'm going to say if you're in doubt, just get rid of it. But the important thing is if we're getting rid of it, we tell somebody so we get it replaced. Otherwise, we're going to have not very many slings around. Some slings and hardware or below-the-hook lifting devices require inspection before each use and observation during use. Well, you should always be observing during use because you're paying attention to what you're doing. And that way you also know if you've created any harm while doing the lift you're doing. Sharp edges, snags, whatever it might be. Keep an eye on it. Any condition that causes doubt as to the strength of the slings, hardware, or below-the-hook lifting device requires immediate removal from service. So if you do not like it for some reason, take it out, tell your supervisor, and they can replace it or send it for inspection. Periodic inspections must not exceed 1 year, so we do ours quarterly just to keep it simple and so we can color code them. Thorough inspection by a designated person based on frequency of use, severity of service, and the nature of the lifts being made. Again, that's why we decided on quarterly. It's just easy to track, but it's not overwhelming, and that doesn't relieve the end user from having to do their previous inspections. Slings, hardware, and below the hook lifting devices should be stored where they will not be subject to damage or extreme temperatures. So again, have a storage place, a rack, whatever it might be, the back of the toolbox, back of the tool bench. If damaged, they should be immediately tagged out and removed from service and physically altered to prevent use. So in the case of slings, we cut them so they can't be used after they're taken out of service. And repairs can only be done by manufacturers. Workers must not use makeshift or unrated slings, rigging components, hardware, or global lifting devices. So yeah, don't weld a piece of pipe onto a bolt and use that as an eye bolt, or manufacture whatever that creative thing. Oh, the other fun thing about this is that looks like a carabiner you get at the friggin' impulse buy at, I don't know, Canadian Tire, or the dollar store. It may or may not even be rated for lifting. Who knows if that chain's rated for lifting, and whatever that creation at the bottom is. I'm sure it is candy, but it's definitely not by the book. So, and we've had these come back from clients. Some of the service units get those. In that case, we don't do anything with it because the client owns it. But people are out there doing this stuff, so just be aware if someone hands you a makeshift, homemade gizmo, maybe don't use it. Workers must not use rigging or below the lifting devices which in unauthorized ways or make unauthorized modifications. So in this case, it looks like someone took a completely legit eye bolt and welded a bolt to it, maybe different threads. I mean, one might be metric, one might be imperial, thought they were making it any better. In this case, well, there's no way that eye bolt is not properly secured. We got nuts, we got space, and they're pulling it at 90 degrees. It's just going to bend right there if it doesn't break. Yeah, don't just get creative. Make sure you follow all the rules. And one thing we're going to see over and over again in this course is it's not so much each individual problem, it's when you start stacking problems. You might have a couple of nicks and scratches, some UV damage, some chemical damage, some weld spatter, whatever it might be. When you start compounding all those things, now you've taken your sling to basically have no braiding capacity, and you just have no idea what it's capable of. Obviously, keep out of crush points, never stand in line or next to slings under tension. That's something good to consider. If you're lifting something up, and try to avoid standing in what would be the firing line if that sling broke. If it was to break, it would move like a whip. It would definitely hit you pretty hard. Things can explode, pop, whatever. Never stand or pass under a suspended load. That's pretty self-explanatory. We should never be underneath something that's suspended. The best example we had of this here that I've seen was someone thought they were doing a good thing. They picked up a chuck plate with the crane and then proceeded to stand right underneath said chuck plate and paint it while it was hanging above their head. So really efficient, not really smart. So don't do that. Yeah. Different types of slings. Synthetic web slings are very common. Our favorite ones around here are the polyester round slings, at least in assembly, which is 3/4 of the friggin' facility. Alloy steel chains and wire ropes. Clark, do you guys use wire ropes? Probably not, eh? No. You use a lot of chains and magnets and whatnot. Yeah. All the metal stuff, because welding is not necessarily forgiving for polyester slings. It's a crappy environment. I know you guys have your isolation slings that use the synthetic web slings, but they're replaced on a reasonably regular basis, and they're super over capacity for what they're doing. So, yeah, consider your environment when choosing your slings. Most of the slings we have around here are the polyester round slings. They're easy, they're convenient, they're cheap. They're only $15-20 for an average 4 or 6 foot sling, so they're not very expensive if you need to get more. Rated load is the maximum allowable working load established by the manufacturer, so obviously everything you use should have be identified and have all this information on it. And don't go over it. We have the luxury of having an awful lot of slings around. There should be no problem finding the right one for the job. We shouldn't need to cheat. If you're out in the bush running a picker truck or something, a service rig, yeah, you might be stuck with a couple and have to make do. Around here, we don't have that problem. We are good to go. Safe working load is also known as the capacity, safe working load, and working load limit. Rated load is calculated as a percentage of the braking strength, which is measured the load required to break the rigging component. They're going to reference a video here they don't actually have. It's just a video showing how these machines work, but this is what they use to test slings. It's a straight pull with a pneumatic, it's got a hydraulic system here that can give a nice, straight, consistent pull and measure exactly how much force is being applied. It's a lab environment basically for testing slings. So that's under perfect conditions. Obviously the workplace is not perfect conditions. So our slings might not, after some use, might not have the same strength. The rated load is calculated by dividing the braking strength by a design factor. So they are over-engineered, but we should never go by that because that's, again, only under perfect conditions. The design factor is the ratio between the design braking strength and the rated load of new unused rigging, and that's the main thing, is that's new and unused. After you've used it and taken some damage, taken some hits, it won't have the same strength anymore. The design factor for the standard slings is 5-to-1, so in theory it'll take 5 times what it says on it to break it, but again, that's only in a perfect hole, only in a perfect environment, and only a brand new sling. So the safe working load is 20% or 1/5 of the braking strength. On chains, it's 4-to-1, so it's 25% for braking strength. In Alberta, rigging must not be subjected to a load of more than 20% of the braking strength, so that's right out of the code. So that's your 1/5 of the weakest component of the rigging, and that's a huge thing to consider too. Whatever you're using for rigging, however many parts and components you have to use, it's only as good as the weakest component. So yeah, we'll get some examples of that later on. Fatigue rating, we don't worry about fatigue ratings around here, but it can fatigue rate by 8%. My rule of thumb is I always ensure that the rigging I'm using is capable of supporting the entire weight of the load that I'm lifting. If I'm lifting a 10,000 pound object, I want each sling to be rated for 10,000 pounds. It's super easy to achieve around here. It's not to say that if one breaks, the other one's going to hold it, because that isn't quite how it works. But at least you know, regardless of any damage it might have or any derating or what have you, if you've got 2 10,000 pound slings on one 10,000 pound object, you're probably good. If you've got 2 5,000 pound slings on a 10,000 pound object and there's damage or issues, you could actually run the risk of having problems. Working load limits are based upon the material strength, the design factor, the type of hitch you're using, and that's an important one. The angle, that's also very important. The diameter and curvature of the sling contact, so your sharp edges and radiuses, and destruction testing done in lab-controlled testing conditions, which will never be duplicated. And that's just it. We can't replicate perfect conditions because we're a real-world situation where things change, things move, different people, different approaches. Instantaneous changes such as rapid acceleration or sudden stopping constitutes shock loading, and working load limit, as stated, does not apply. Shock loading is hard to quantify. Everyone's going to be different. We need to make sure that we're not dropping things, having things fall, because that will overload things in a hurry, especially if those things are not in mint condition. So slings must not be used if they appear to be damaged. So there's varying degrees of damage. Obviously, most of our slings don't look perfect. But if we start seeing consistent problems or multiple problems, again, take them out of service. There's no point using something we think that's not in good shape. Slings must have suitable characteristics for the type of load being lifted, the type of hitch being used, and the environment. And the environment's one of the biggest ones. We use different materials because of different environments. Obviously, welding uses metal because welding's a pretty harsh environment, whereas production and assembly are going to use nylon and polyester slings because they're nice and soft and easier on the powder coat. We don't want to use clamps, obviously, on powder coat, and we'll get into all that kind of fun stuff later on. But just consider your environment and the material you're lifting, the type of hitch you're using, and the type of load you're moving around. Rated loads of slings must not be exceeded, so in this case we have our 1,600 for a straight, 1,280 for a choker, and 3,200 pounds for a basket. One thing to note about baskets that we will get into later is that's on 2 hooks. So when you basket back to 1 hook, you don't get 2 times the strength. You only get this. If you're using 2 hooks, it's double. If you're using 1 hook, it's still the same as a straight pull. When a choker hitch rating is not identified on the sling, the choker hitch rating shall be 80% of the vertical sling. So this will be 80% of that. Is basically what they're doing to get that. Or 75% for wire rope. Not that we should really be choking wire rope, unless the manufacturer or qualified person provides other ratings. When using multiple leg slings, ensure no leg is loaded above the single leg capacity. So we just need to be mindful of how we're loading those things up. Single and multiple leg slings must be used in accordance with manufacturer specs for the type of hitch, the capacities and angles stated on the sling tags, and with derating factors applied. Shorten or adjust only by methods approved by the sling manufacturer. Don't tie knots in things to make them shorter. We do have on pretty much all of our cranes the nice chain bridle assemblies that allow you to shorten them. They're fantastic. You can dial things in pretty precisely. There's no need to do anything weird like this or twisting slings or whatever other cheats people have used to make things shorter. Just use the right sling, right chain for the job. Hitch slings to provide control, hitch slings to provide control of the load and prevent slipping or sliding along the load. So chokes are a great way to bind on the load. They have a bite to them, so they will contract around the load and physically hold it. Baskets are the worst thing ever. I try to avoid baskets like the plague. They are slippery, they are slidey, and they're just not a great means of load control. A choke will get you a heck of a lot farther with a lot more control. Load should never be rested on the sling, so we don't want to just put it on the ground and put the sling on top of it. We want to put dunnage underneath it, protect the slings from being crushed. Sling should never be pulled from under the load when the load is rested on the sling cable. A, we should never rest the load in the sling, and B, we would definitely not use the crane to pull the sling out from underneath the object. We're never going to know what kind of force we're putting on the sling or the crane. It's definitely going to damage the sling, could damage the crane, might even damage whatever we're lifting. Avoid twisting slings. Not the greatest example, but still, in a perfect world, every sling should be nice and straight. When you start twisting them, it actually does derate them. It also puts more strain on them in some regards. So again, if you couple that with some nicks, some scratches, some cuts, whatever else might be there, and then start twisting it up to boot, it's not going to hold as much as you think it's going to hold. Don't choke on the eye or the base of the eye or splice. So basically, the rule of thumb is put the tag to the hook. Every sling's got its tag on it that shows, well, like that one there, and shows the information. We want that to be on the hook side. In this case, get a longer sling. Unless you're worried about how much headroom you have between the ceiling, like maybe you're doing something at the top of the manipulator. Otherwise, around here, headroom shouldn't be an issue. So just get a longer sling so this choke winds up down here and not on the splice or on the tag, because that'll damage the tag. It'll potentially damage the sling itself. Use more than one sling for better load control. Good rule of thumb is use at least two, and if you can pull it off, use three if the thing is not a symmetrical load. 3 slings is always your better way to go. Obviously, if you're only using one, it has to be perfect, and if anything changes, it's going to fall. Whereas if you use 2, like on the right, it's going to be nice and easy. And again, because it's choked, it's not going anywhere. Slings should not be constricted, bunched, or pinched by the load hook or any fitting, so use properly sized rigging for what you've got. If you've got big shackles, use big slings. Otherwise, you want to run the risk of point loading things. Conversely, if you had a tiny little sling that only took up the middle, now all the force is going to be on that one little point. This would be bad practice anyway. Ideally, we want to have the sling through the bail, or through the loop. But either way, just consider how everything is sized. You want to make sure that if you have small shackles, use small slings. Vertical hitch, different types of hitches. Your vertical straight pull, so regardless of the shackle, it's just right through the eye of the sling, right back to the hook. A choker, loop it around the object, back through itself. And one thing to note when it comes to chokers, there should always be that gap there. We don't want to hammer this down so it's tight. We want to leave the gap so that this piece here is nice and gradual and not bent right over really sharp. And of course the basket hitch. But again, this is a basket hitch, but because it comes back to one hook, you're not actually getting a double. You again. That's okay. You're allowed. It's all right. Consider the load finish surface. So, I mean, around here, we don't do a lot of stainless, but stainless is obviously slipperier or slidier than carbon. Big thing to consider around here is the weather. If we bring something inside in the winter, it's going to be cold, it's going to be condensation, it's going to be slippery. So it's helpful to either warm it up and leave it overnight, let it warm up, use a torch, whatever, try to get that condensation out of it or off of it. But always consider what you're lifting and how it's going to slip or slide on how you're going to lift it. Vertical hitches are a straight line, your straight vertical hitch or a vertical hitch with angles. Angles do drastically affect the amount of force being put on the slings, and we'll get into that later on. It's actually amazing how much angles make things heavier, or the physics of them make things heavier. Obviously, if you're using one sling, that sling's taking the entire weight of the object. Pretty straightforward. Choker hitch, so we want to make sure the capacity tags, this is where you put the tag up to the hook. You wouldn't want to have it down here against the object. It just takes undue stress and wear. And then you want to have ideally a nice 120 degree angle here, and not some crazy angle because you hammered down the choke or the bite. There's a lot of leaks here. Shit everywhere. Yeah, don't beat down the hitch. I know this is something I was taught out in the field. Oh, just hammer it down, make it nice and tight. Yeah, no, in a perfect roll, we don't do that. If you need to, do a double wrap so you can get better contact. As the angle of the choke decreases, the capacity of the sling decreases. So this is a good example of why we try to avoid that. At your nice 120 degree, which gives that nice gap right here, there should be a hole. That gives you 100%. As you start to beat down on it, you start to drastically affect how strong that sling is. Some of these approaches might be necessary if you're rolling something, but then you should take into account just how little that sling is rated. When you go all the way down to zero, if you take this thing all the way around to here and there's basically a 0 degree angle, you're only getting half the capacity of that sling. So if you've used a 5,000 pound object with a 5,000 pound sling, well, now you're down to 2,500 pounds capacity on your sling without even really knowing it. So whether you remember the numbers or not is kind of irrelevant. You can always reference them in the book or online later. But just know that if you're taking that angle out from the nice 120 degree from a perfect choke, and you're trying to get the most out of it or roll something, you've lost an awful lot of your capacity, and you should rig accordingly to get a better or a stronger sling, I guess, if that's something you have to do. A single choker hitch should not be used to lift loose material or any load that could tilt. Absolutely, this is poor practice. You just put two on it, spread them apart. When two chokers are used to form a rigging triangle, the load will be much more stable. So a single wrap choker, there's that nice 120 degree angle there. They're showing us with the nice gradual angle here. That's what you want. If you do require 360 degree contact because of the load itself is slippery or whatever, you just need a bit better control, you can do the double wrap, but you still maintain that 120 degrees and don't hammer this down to get more contact. This is a good trick if you find yourself with needing, like if you do need to have short headroom, or if you only have one sling available. I've used this in the field a whole bunch because it works really well. You get just that extra little bit of control because you can get a little bit of space between these. Now I was taught to do it the wrong way, but the right way to do it is to put the center of the sling back through the eyes and to the hook. So, but this does give you more control if only one sling is an option, or if it's what you need to do for some reason. Just try to avoid doing it on the way on the right, where you put the eyes back to the center of the sling. This is an interesting trick if you ever find yourself in a position where you have to make something shorter, or I guess dial it right in. You can actually make or hook the sling over top of the hook, and then run the eye back through the eye, and then back up the hook, and you can kind of slide this along to make the sling longer. Again, if you're running a picker truck out in the field or something, this stuff could be kind of handy. Around here, there's not a lot of need for this level of creativity, but it's a good trick to have in your back pocket, I guess, if you ever needed to do it. Basket hitches. So a true basket hitch, like it says, like it shows, goes to two hooks. That's how you get your double. A modified basket hitch is what was more commonly used, but that's where it goes around the object and back to one hook. So that's where you get your 200% capacity, is with two hooks. After that, we start to lower it, and the sling angles start to play into effect. The lowest capacity basket hitch is going to be a pretty tight one, where you only have 30 degree angles. So just take into account, you're only getting your 200% or 200% capacity if you're doing it to two hooks. So two basket hitches provide average load control. Around here, there's not a lot of cause to use two basket hitches. This might work if you work in a foundry or a steel mill or something where you're moving loads of metal across a shop with a spreader bar or multiple cranes or what have you. Around here, we don't have a lot of cause for lifting things like this because we're usually using one hook And basket hitches on one hook don't work very well because you really don't want to have sling angles when you're using baskets. So this is a perfect example. Like, yeah, it looks good in the picture, but it'll only be a minute before that happens. Because anytime you start involving angles, the physics demand it's pulling together, and that's the risk that's going to happen. Then you're going to drop your load, and because it's only a basket, it's just going to slide right out. So if you're doing something along these lines, go the extra mile, put a choke on it, then it can't go anywhere, and you won't wind up with the problem on the right side. Or you can do a double basket like this, where you loop it around, and that's basically giving you a choke anyway. It's constricting around the object. So inverted basket hitches, don't do it. The only time you should be doing it is if you're using other slings to control it, so that the other one can't seesaw and move around. I'm sure this has all been done by people. Plus, realistically, you'd have to have eye bolts or something to be actually attaching these two, the shackles or something like that. I guess with our equipment, we have engineered lifting points, so maybe you could pull it off. But realistically, with all the chains and stuff we have, there should never be a need to do an inverted basket hitch around here. Get into the characteristics of the slings, web sling characteristics. They're lightweight, and what drives the decisions for picking which one's best for you, in a lot of cases, is going to be money. That is what drives the world. If we don't need to invest in the fancy stuff, we're just going to use the cheap stuff, and that's fine as long as we know it's going to work for whatever we're doing. Web slings are lightweight, flexible, and easy to handle. They won't damage load surfaces, and that's a big one if you're working with finished goods. Welding doesn't have to worry about that because it's all raw goods or unfinished weldments. But assembly is definitely going to consider damaging the nice powder coat. They can adjust to the load contour with tight non-slip grip, and they have some stretch to allow for cushioning against shock loading. All the different styles, type 1, triangle, and choker. So this one's designed with this one to loop back and go through here to give you a nice, proper choke. The most common ones we're going to have around here are going to be these ones, the twisted eyes, just because of the way that they loop around stuff. We might have the flat ones. Identification is going to be on all of them. You should have the name or trademark of the manufacturer, manufacturer's code or stock number, rated load for the type of hitch and angle it's based upon, and the type of synthetic web material. So depending on your environment, if you're working in an acidic or basic or caustic environment, you need to know what kind of, or in an explosive environment, you need to know what it's made out of to make sure it's not going to cause any sparking, it's not going to be worn out by the atmosphere, and then the number of legs that are required. So in this case, it's showing us a true basket back with the 2 hooks. Yeah, and if you can't make out the information on the sling, the same thing. It doesn't matter if the sling is in mint condition itself. If we can't read the tag, take it out of service, get another one. How to inspect it: examine each part of the sling visually and by hand, making sure to expose and examine all surfaces. So you really want to bend it, twist it, flex it. You want to make sure that this place where it's tied together is all properly sewn together and there aren't loose strings popping out or anything like that. Make sure it's all properly attached. Look for embedded particles. Machining would be a perfect place to wind up with embedded particles. They have all kinds of swarf floating around there, bins full or hoppers full of metal filings and whatnot. So it wouldn't be shocking if they had metal embedded in their slings. Wearing gloves is a good way to protect yourself against that risk. What to look for: unreadable tags. If you can't make out all the information on a tag, the sling's no good. Look for melted or charred fibers anywhere on the sling. So obviously, looks like we got some slag on there from welding potentially, or just general heat damage. Look for nicks and scratches. You're going to see a lot of this on some slings. 1 or 2, depending on how deep these are. They're not awful, but if you've got a whole bunch of them, well, it's a compound problem. Again, if you see something you don't like, check with your supervisor. Every sling, well, a lot of these slings will end up having some minor damage, but that's also why don't use a sling that, if you have a 5,000 pound load and you have a sling that's rated for 5,000 pounds that has a few of these, well, that sling's not rated for 5,000 pounds anymore. We don't know what the hell it's rated for, but we definitely can't trust it's rated for what it says it's rated for. So if you use a sling with a higher capacity that has a nick in it, again, odds are it's going to be fine. Most of you have done this long enough to know what you feel comfortable with doing. If you're new to this and you aren't comfortable, stop and ask questions. That's the best thing you can do. We have a whole lot of competent riggers in this place, and we can always learn by asking questions if we see something we don't like. And the other thing to consider with all of these problems is it's not that you're going to have one problem, you're going to have four. So you're going to have a little bit of heat damage, you're going to have a nick, you're going to have a cut, you might have some wear from binding, you might have a few broken fibers, whatever, and it's all that, it's cumulative. So now all of a sudden your sling is basically garbage, but because each little thing adds up. Then you add something crazy like tying a knot in it, and your sling's basically garbage and isn't rated for anything. So yeah, the little mixed fibers standing out from the rest of the sling surface. Broken fibers of equal length indicate an edge cut. All fibers in synthetic web slings contribute to the overall strength. Yeah, it's got the strength it's rated for because it's so many fibers, just like a wire rope. It's some of its parts, and if its parts are weak, well, the whole thing's weak. Loose or broken threads in the main stitch patterns. If the stitching is not fully intact, the strength of the sling may be affected. Same kind of stuff you'd look for on fall protection here. You want, except in that case, it's literally your life hanging in the balance, no pun intended. But you want to look for this kind of stuff, make sure the stitching is all good, give it a twist. One distinct advantage, well, up until recently, one distinct advantage we have here is you don't have a night shift. We have a night shift in machining now, but for most of us, we're the masters of our own environment. The only guy working in your bay is you, I think. Nobody comes in and uses your bay when you're not there, right? Really? No. So you know what the stuff you have in your bay has been through, so you know if it's in good condition. Assembly doesn't have a night shift, but they do share tools. So in that case, doing a quick check before you use an object in an assembly is probably more valuable than Clark double checking on something he's had hanging in his bay all day, and he knows what it's been through. You might be grabbing something he used, so you never know. But the saving grace of not having a night shift is no one's coming in and doing a bunch of stuff in our absence, and especially if it's an environment like Clark had a night shift, he'd have a guy in his bay welding and using his stuff, and when he gets in the morning, it's not where he left it, or it's not in the state that he left it in. So consider that when you're considering all this stuff too. Same thing with the pre- and post-use inspections. Well, if you're the only person using it, you know where it's been and what it's been through. So this is probably the most common look for slings around here. And once they start looking like that pretty bad, we want to get rid of them. Just any general wear, if they feel fuzzy, indicates the fiber's been broken in contact movement along rough surfaces. Again, that's probably the most common thing we're going to see around here from things rubbing. Obviously, if there's any knots, that's a no-no. Knots are hard to get out to begin with if you pull things really tight, and it basically derates the sling by up to 50%, which is definitely not good if you're already pushing the sling to its max. And then you add a couple of nicks and scratches in there and some wear, this sling's basically useless. Look for fading. I mean, UV is a big thing. Or in most of our shop, UV is not an issue. Welding is, again, one example where UV is going to be a thing because they're creating their own UV. So if you do have slings hiding in your bay or something and you're welding next to it all day, you're degrading those over time. I know when I was out in the field, we had to make sure we put our stuff back in boxes and stuff and kept it out of the light so it wasn't exposed to the rain, the wind, the UV all day long. Don't constrict or pinch or bunch or pinch slings. So this is kind of like the pictures we saw earlier on, and this is why. Because when you do use it and apply force, it's going to basically create heat. It's going to melt. It's going to wear out. It's going to point load. It's just bad for everything altogether, so avoid doing that. And you're going to wind up with slings that look like the one on the right. When it comes to putting an object in the eye of a sling, it should not be wider than 1/3 the length of the eye. So in the event that this eye is 3 inches, we only want a 1-inch piece inside there. We don't want to jam a 3-inch pipe in a 3-inch eye, as an example. Because it's going to stretch everything. It's going to run the risk of buggering up the stitching here where the splice is. It's just not designed to go that way. So take that into consideration. And you'll see radiuses and diameters come up a lot. And whether or not you remember the exact formulas is kind of irrelevant. It's just know that these things matter. And if it looks wrong, it probably is wrong. So don't jam an object inside the eye of a sling that maximizes or stretches the eye all the way out. Tags and labels should be kept away from the load, like I mentioned earlier. In this case, unless you had some weird issue with headroom when you lift up, get a bigger sling. Or you could take out the double wrap or find something else, but a longer sling by 2 feet would ensure that this is up. It's still attached to the hook, but now it's up higher and it's not part of the actual choke. That's going to bugger up the tag, plus the tag itself can do damage to the sling. Just bad practice. Ironically, with those continuous slings, it's actually can be awkward trying to get a tag to not be part of the lift. Whereas with regular slings, it's actually pretty straightforward, because 9 times out of 10, if you put the tag on the hook, you're not going to have an issue. Things to consider, and this is true for everything: temperature, any chemicals in the environment, temperature around here, assembly and welding. Welding's obviously going to have hot things, so we have to be mindful of that. We don't want to throw a polyester sling on a hot welded surface; things will melt. Conversely, we do deal with bringing things inside during the winter, and then you're going to have cold objects, condensation due to the cold coming inside. So consider that. Chemicals aren't really a big deal around here. We don't have to worry about it, but that could be an issue if you ever go somewhere else. So just consider your ambient temperature, the temperature of the object you're lifting, especially if you were just melting it 5 minutes before, and anything coming in from outdoors. UV light, so fading, stiffening, shortening, reduction of the elasticity. So yeah, sun and UV actually has a pretty drastic effect on the condition of the slings. And moisture. I mean, I've done a lot of rigging in the rain. It isn't ideal. Obviously, it loses 15% of its strength according to this. Well, it's wet, so you have to take that into consideration. Not that we ever did, but it's good to know. And if you do get your stuff wet, hang it up to dry. Don't use it till it dries out. And if you have to, you can always use metal chains and stuff. I don't have this video. This is just a little video that shows the perfect braking in those machines. I'll see if I can find it at some point, but I haven't got it right now. I don't know why they didn't include it, but it's not there. I'll just work with videos. Do any of you guys have to hit the gut truck? Okay, so whenever it comes, when it comes and the horn goes, we'll just take our 20-minute break at that time. Because it comes down here, so you can just go visit it, and then we'll just all take our break at that time. Polyester round sling characteristics. They're a continuous loop of 100% polyester fibers enclosed in a protective cover. So kind of like a wire rope. It's a whole bunch of little tiny fibers wrapped up into the inner core with the outer jacket on it. These things, there's different criteria for inspection we're going to get into. The cover abrasion will not reduce sling capacity. So we can damage that outer sleeve, the jacket, if you will, but that won't affect the inside unless we cut right through both. And one thing about these is they're deceptive because they can hide damage. That jacket slides freely around the inner core, so this can slide all around, which is great, but that also means if you cut it right here and then you slide the jacket, now you've got the cut on the inside, but the visual cut is over there. So the only really good way to inspect these things is to use your hands and go around the entire thing. There should be one bump on the inside where the fibers are knotted together, but as we discovered when we tested those brand new slings we bought, you found a second lump. Now because they were brand new, we kind of put that, well, yeah, it's probably just another connection point, but if you're using these things, you should only really find the one, and if you start finding other bumps, it's because there's probably damage on the inside that you can't see. If you're in doubt, throw it out. These little 4-foot or 6-foot slings, they're 10 or 20 bucks a piece. They're not worth very much. So if we don't like them, get rid of them, get new ones. I usually have a spare supply. Like I say, Jacob just bought a whole bunch of these for assembly. But inherently, the cover abrasion won't reduce the sling capacity if the damage is only on the cover. Wear points can be rotated to extend sling life. Yeah, to some extent, but it's just moving the wear on the outside around, away from the wear on the inside. So these things are problematic. If you don't like the way they look, take them on a service. They are really easy to remove chokes. You don't get bunched up very much. And smaller hardware diameters reduce the weight of load. And we'll see this later on. But if you're putting a sling around something that's a 1/2 inch diameter, well, that binding that it creates is actually bad for the sling. So take that into consideration. Same things we're going to see on everything else: the name or trademark, the manufacturer's code, the rated load for at least one type of hitch, the core materials. So again, they want you to know what it's made out of, the cover material if it's different, and then the number of legs or if more than one. Again, this is showing your nice 90-degree basket, but that's showing 2 hooks. So examine each part visually and by hand. Again, you kind of want to feel around the entire thing, looking for the problems. Feel the fibers along the entire length of the sling. things to keep an eye out for, obviously cuts, and if you've got to cut that bad on the outside, it stands to reason you probably got to cut on the inside as well. Holes, tears, cuts, embedded particles or materials, excessive abrasive wear, snags, and exposed core yarns. Follow the web sling or tie-down association's requirements for round sling protection when in direct contact with edges. So this will be softeners that we'll get into later on. Bearing stress or contact pressure between the sling and connecting hardware. So that's a matter of the radiuses. Again, we'll get into this stuff later on here. Suitable connection hardware sizes for polyester round slings. So this is just telling us that like a round sling size of 1 inch should have effective contact of 1 inch with minimum stock diameter of 7/16, which is basically half an inch. So you can't just take a big sling and wrap it around a small object. Again, this is the kind of stuff I don't expect you to remember it. I know I don't remember it, but a nice gradual loop is what you want to see. You don't want to see anything bound too close. With our weldments around here, we should try to use a shackle and not just put the sling right through the engineered lifting point. A lot of those points have sharp edges. They're also very small radiuses. Those two combined, the small radius with a sharp edge, is a surefire recipe for cutting a sling, especially if things move in a way we don't expect and slightly shock load things. Effective contact width, so straight bearing surfaces, effective contact width is equal to 100% of the actual inside width. So in a perfect world, we want to use the entire pin on the shackle. We don't want to put a shackle with a 3-inch pin and then put a 1-inch sling on it. We want our sling to cover pretty much this entire thing and size our whole rigging set up accordingly so that everything fits nicely and isn't point loading. If you put a tiny little narrow, say, wire rope sling on here, it would point load all on one place, or it would capsize, and that's not the way they're designed. So we want to make sure we use a sling that's going to fit that properly. Again, perfect world situation. Your curved bearing surfaces, effective contact with the 75% of the actual inside width. So again, you don't want to put a tiny little thing on the shackle right here. You want to make sure it goes, you know, and covers most of it, so it spreads the load around and doesn't point load anything. So in a perfect world, we want something, you got a 4-inch shackle, we want to use a 3-inch, that's your 75%, but 4 inches, I wouldn't go down to a 1-inch because that's only going to be 25%, and then you're not using the shackle properly, and you're putting too much strain on one small part of it. So basically everything should be sized accordingly, especially if you're lifting heavy things. Alloy steel chain characteristics, they have long service life compared to synthetic slings. Yeah, they're rough, they'll take a lot of abuse. But that being said, you can still screw them up. We had the weld spatter issue in welding. We've had bent links and all that because they were put around sharp corners and then pulled pretty hard, obviously. They resist impact, cuts, and abrasions. They can be used in oily or dirty environments, which is important if you're working in machining. Oh, look at that. So let's take 20 minutes. That gives anybody who needs to go to building 2 time. We'll come back at around 10 after 9. These ones have their shorteners equipped. This one does not. So only 2 grades of chain are actually rated for lifting, and that's 80 and 100. This is why you can't just go buy chain at Home Depot and lift things with it. I mean, you can try, and it might just work. But when it comes to all the stuff that we're buying that's designed for rigging, you need to have it be grade 80. So in this case, it's got the 80 right on it. Alloy steel chain, high strength alloy steel chain, which is heat treated. That's the main thing. The optimal word is heat treated. All your other cheap shit you get off the shelf probably isn't. There's grades for tie downs and all that, but the rigging chain has to be 80 or 100. The difference being is 100 is higher strength, lighter weight. So it's all a matter of money. If you have, I don't know, like Mammut, the guys who move entire modules and bridges and all that shit, probably use 100 because they have 2 tons of rigging in their assembly. Whatever they're lifting, they're also lifting 2 tons of rigging. So saving 25 or saving weight will be beneficial when you have all that. Most of our shit, I would assume, is 80 because we don't need to save a half a pound or something. We're just going to use the cheaper of the 2. But this is higher strength, heat treated, uses a variety of tie downs, and 25% higher strength. So you get more strength have the same size chain, so you get it's basically lighter weight. And again, it's all a matter of money. If you want to pay for it, you get the good stuff. Different parts include the collector ring or master link, the identification tag, the chain shorteners, the chain itself, the coupling link, and the hook. Should have all this pertinent information on there. You know, Continental conveniently is the same place we get most of our stuff from. You got your size, your load, your capacity, the serial numbers, the type that it is, the date that it was manufactured, and how long it is. Make sure to examine each part of the sling visually and by hand, making sure to expose and examine all surfaces. So to do a proper inspection on chain slings, you have to get in there and move every single link around, looking for damage such as this, where things have actually bound and worn, or spatter or what have you, cuts, heat damage, things that are miscolored because they've been heated up. Any damaged or unreadable sling identifications, excessive wear, nicks or gouges, yeah, those ones are awfully excessive. The grooves that have been worn in these are insane. You definitely wouldn't want to see that in use. Deformed, bent, or twisted links, we have seen that come through around here, presumably because it was wrapped around the corner or something and then it ended up being bent. Heat damage, in the case of that one, looks like someone hit it with a cutting torch. That's definitely not what you want to see. You might also see just miscolored linkages where they were heated with a torch but not actually cut. That'll take that heat treatment out of them and make them much more pliable and potentially break. Any lack of ability of the chain to hinge or articulate freely, so if you've got a stretched link like that one there where things can't move the way they're supposed to, that'll cause uneven wear, uneven loading, and that's a no-no as well. So again, anything that doesn't look right, it isn't right, and if it can't be repaired, it can be replaced. Weld spatter, again, whether it's fusing the links together or just on there, the welding spatter is hot, and when it hits there, it can affect the structure of the metal. So we don't want to have that on there. It might make for weak spots in the chain. And again, any visible damage or condition that causes doubt. So when it comes to chains, we have to be mindful of the diameter of the chain itself and what we're wrapping it around. This is how we can avoid bending the chain. It should be a nice gradual arc around the object. In this case, the small d being the diameter of the chain, and the big D is it's 6 to 1, basically, is what I'm getting at. In this case, you've got a 3-inch object and a 1/2 inch, so half goes into 3 6 times. So that's your optimal condition for radius and the diameter, and that just makes sure everything is sitting nicely, everything lines up nicely, nothing is caked too tight. Again, whether you remember this 6 to 1 or not is debatable, but just know that if you are wrapping chain slings around an object, it should not be a 3/8 chain wrapped around a 1-inch object. That is going to make it bend and bind and do all kinds of weird things. It needs to be a nice, gradual, and perfect rolled 6 to 1 comparison. Point loading occurs when the chain contacts edges of a load, resulting in loss of strength. This is how things get bent, and not to mention that the load then can get damaged. So use edge protection if need be, or find a different means of lifting it. When it comes to the radius of a corner, we have similar rules apply. The load radius is 2 times the chain diameter or more. The load factor is 1. So it's a matter of the way things sit on the corner of an object. You've got a nice, easy radius. There are radius gauges you can get to test the radius, not that you really need them. You can probably visually tell roughly what it is. And you can just tell by the way the chain's sitting. In this case, it happens to make like a nice 45 degree when you've got the link sitting against it. Edge protection is going to help. Just don't wrap chain around really tight objects because it'll cause damage to the object and run the risk of bending the chain. If the load radius is larger than the chain diameter, the load is 0.7, so this is where you've got a sharp corner. Now you're kind of point loading it, and it's going to put undue stress on that link. So it's only getting 70% of what the capacity tag says. And here you're going all the way down to half when you have a straight 90-degree corner with no radius at all. It's potentially point loading it directly against that particular link. That's how you get links to bend. So that's how drastic things can be. For multi-leg bridles, ensure they're properly seated, that they're fully engaged. The hook tips should be facing out. This is something we're going to see over and over in this course. When you put a hook through an object, the hook tip should be on the outside, not the inside. When it's on the inside, it can run the risk of rolling out. when it's on the and it can run the risk of point loading. Whereas here it's seated properly. And again, we'll see that over and over. You'll harp on it a fair bit. No twists in the chain, so that can be hard to achieve. You know, one little kink isn't going to likely be a problem with that, again, unless you're running things right to their maximum capacity. But you don't want to like twist the chain to shorten it, or have a bunch of twists in your chain, because now that's putting undue wear and tear on the chain itself. Don't cross any of the legs over. Don't cross your legs, and don't exceed single leg capacity. So again, make sure there's a proper fit. The one on the left is nicely fit, everything's seated properly. The one on the right is obviously not sized correctly, and it's point loading on the edges. Definitely not what you want to see. You want to make sure everything is sized accordingly and everything seats properly and has a nice fit. Same problems as anything else to consider. Consider your temperatures and any chemicals in the environment. Again, not just the ambient temperature of the air, but the contact temperature if you're working with hot or cold objects. Cold metal is inherently slippery. Wire rope, lighter and less expensive than chain, but still hard wearing. The steel construction resists cuts and abrasions. Utilizes multiple wires to carry the load. This is, of course, what all of our cranes use for the most part. Stiffness allows for insertion through openings or under load. So the one saving grace to a wire rope is you can push it. You can't push a nylon sling. You can't push a chain, but you can push a wire rope. External conditions are easily inspected, so you can tell right away or pretty easily if it's in good shape or not. Different styles include the eye and die, the eye and hook, and I know we have the eye and hook styles around here. It's pretty much all we really use. We don't use a lot of wire rope around here. The endless style and the bridle assemblies. All the different parts. You have your individual wires, which get put together to make a strand, and then the strands wrap around the core. One lay of the rope is the distance it takes for the rope, the strand to go one time around the core. If you go through trade school, they'll teach you a whole bunch more about this stuff that you may or may not ever use, but you'll see it over and over again, especially in first year. It all affects the way it twists or doesn't twist. Always wear gloves when doing inspection for sure. The wire ropes have little pieces sticking out. I know they recently, they've replaced a few wire ropes on the chain, on the cranes in welding. I think those ones are probably the most heavily used cranes in the entire facility. So they take more shit and abuse and end up having problems like this happening. But often they're not found until the crane inspectors do their inspections, because you have to really maneuver that wire rope and twist it and bend it and push it to try and expose any inner breaks that have occurred. If you're lucky, they'll be obvious like the one on the left. If not, they'll be kind of like this, or worse yet, you won't see it until you twist it and kind of separate the strands. So they can take a little more farting around. They do a good thorough inspection on wire ropes. Broken wires, again, and when they're covered in grease to boot, that can be kind of hard to see, so you have to take the time to do a pretty thorough inspection. Severe localized abrasion or scraping, hopefully it's pretty obvious, but like the one on the bottom, odds are you're not going to see that, especially if it is covered in grease or lube. Bird caging and kinking is a little easier to notice. I know a few years back we had a problem with the wire ropes that are used to support the doors in assembly. We're actually doing that and getting pretty bad. Thankfully caught it before it became a problem. Bending or kinking is pretty self-evident. If you've got one that's kinked, just take it out of service, don't use it. That comes from that whole radius issue. Again, if you've used it incorrectly around too tight a radius and then pulled on it really hard, you can get things to kink and permanently deform. So protect slings with materials of sufficient strength, thickness, and construction to prevent damage to the sling. In the case of the beam, they've got special softeners that go on the beam and go around it to give you a nice, gentle radius instead of point loading against the end of the beam. I know in the field we used to just cut chunks of 25 to 1 knots debatable, but just know that for a wire rope it has to be a pretty gradual bend to avoid causing damage. The chain was 6 to 1, this is 25 to 1, so if you put this thing through a shackle and then pull on it, you're probably going to kink it, because that's definitely not going to be 25 to 1. When is edge or sling protection required? All slings can be damaged. The edge does not have to be razor sharp to cause damage. Slings can be protected from damage and cuts at abrasive surfaces. So some slings have a level of built-in protection. They have a buffer on the inside of the eye or a wrap around the outside of the eye, or in the case of the one on the right, there's no protection whatsoever. Most of ours are usually unprotected. We might have some with the eye wrap. Again, a lot of ours are the continuous ones, so it's less of a concern. They have built-in protection. There's all manner of different softeners available. I know we like the ready sleeves around here. They're probably the most convenient. The saving grace of the ready sleeve is you can put your rigging on your object and then put your softener where it needs to be. All the rest of these, you have to have the softener on the sling before you put the sling on the object, which can be a pain in the ass. And these things are dirt cheap. The small ones for 1 and 2 inch slings are only $5 or $10 a piece. I've got a whole stack of them in my office. They're cheap to have around. Better to have them than not have them. And if you need them, ask for them. They're very handy. Different levels. I mean, this one has built-in pads to basically eliminate that sharp corner. Again, if there's a market for it, someone's made it. But this way, it creates basically zero contact right on that sharp corner, and all the pressure is applied to the sides or the edges. So there are options available. If you find yourself doing something repetitively and there's an option for a better tool to be employed, talk to your supervisor. We're pretty easygoing about getting the right things. There's the sleeves like this, like a Kevlar sleeve that can go around the entire sling to protect from cuts. So that's the difference. Softeners are not cut protection. They're just to kind of alleviate a sharp corner or a tight corner, a tight bend. Whereas a cut protection is actually a Kevlar, kind of like your Kevlar gloves, same material, that cannot cut when it rubs on a sharp surface like the end of that small pipe there. So make sure you have the right one for the job. All different manners of cut protection that go on beams or different shaped objects, right down to the ones that actually have magnets built into them, so they're kind of self-align and hold themselves in position. Confirm the sling type selected is suitable for the load being lifted. Again, don't grab a wire rope to use on powder coat or a chain to use on powder coat. Use an nylon sling. Consult with the sling supplier for bending strength or reduction factors related to all contact points and interfering hardware. Evaluate the need for sling protection. Check with the sling manufacturer, sling protection manufacturer, or qualified person to determine the suitable type of protection needed. When evaluating potential sling protection material, factors to consider include the type of sling you have, the rigging method, and the load's physical properties. Install the potential sling protection and perform a test lift by raising the load slightly and then setting it down. Test lifts are always handy, especially if you're doing something new or something unique. Bring it up off the ground, analyze your rigging. I mean, most of what we do here is pretty repetitive and stuff we've done before. But if you're doing something new, it's a good thing. You can actually lay it down, take it all apart, analyze your rigging. It's not likely we're going to do that around here, but you never know. Again, if you're doing something big, heavy, or unique, it might not be a bad idea. And sometimes you're going to have to do several test lifts and inspections and evaluations to determine the proper form of protection. It's all relative. If you're lifting something that costs $1 million, you might want to do a few test lifts and get things perfectly right. If you're lifting a weldment onto your bench for the 1000th time, not that I'm advocating complacency, but you probably know you've chosen the right stuff. You still need to be aware of what you're doing and how you're doing it, but it's varying degrees of how much you have to do test lifts every time you do a lift. If you're new to this, like yourself there, Vitaly, if you're new to rigging, every lift is new. So everything you do is going to be the first time you do it. It's never a bad idea to treat every lift like a new lift. And again, if you're not sure, ask questions. All the types of rigging hardware, different types of shackles. So you have a standard shackle, an eye bolt, swivel hoist ring, master links, and turnbuckles. The only time we use turnbuckles here is in our 16Ps. We don't use them for rigging. They're more of a, maybe for tie downs on a truck. They do allow you to actively change the length of things when they're actually under load. So they're pretty, in that regard, they're pretty useful, but we don't use them here. Swivel hoist rings are the best ones if you can get your hands on them because they're super versatile. And they're the same rating in any position. And of course your standard shackles we use an awful lot for just about everything around here. So rigging hardware that appears to be damaged must not be used. Does anybody see the problem with the one left? The other ones are kind of self-explanatory, but
Stretched out.
correct. Yeah, it's not really bad, but we have one full thread right here, and that full thread could be a sharp edge that could cut the sling. So that shackle's actually been expanded. So we won't want to use that. We want to take it out of service and replace it. The eye bolt is obviously nicely bent in half, and this thing looks like it was pinched or constricted, so it's not going to rotate properly. It's in a pretty poor state. I'm not sure if this is buggered up too, but either way, it looks like it's been used pretty rough. The saving grace to these is you can buy new parts and you can repair all this. You can get new bolts, you can get new washers, you can get new bales, and you can repair it. The other ones are pretty much SOL. You've got to toss them out. And again, if you're tossing anything out, tell your supervisor so they can make sure you get a new one. The angle of loading affects the stress on the hardware. As the horizontal angle decreases, the stress increases. The integrity of the load where the rigging hardware attaches is the responsibility of the end user. And you're going to see this over and over and over again. At the end of the day, it's all on you. You're the one doing the rigging. You're the one who's been through the training. If you're doing it wrong, it's on you. If you're not sure, ask. There's no harm. There's no stupid questions. No one's, the guy who says he's the best is the guy you want to stay away from. The guy who admits that he doesn't know everything, fair enough. You can always look it up together. But yeah, if you're not sure, stop, ask, get a second opinion. So again, take into consideration the temperature, if it's hot, cold, whatever it might be. Obviously chemicals, that shackle looks like it's 100 years old and been sitting in a bath of acid forever. Definitely wouldn't use that. Different styles of shackles, anchor shackles, so kind of your standard. Then you have the bolt type with the cotter pin, chain shackles, and synthetic sling shackles. These are just designed to have this nice flat part where a sling can fit through there and be flat against it. Most of ours are going to be the anchor shackle style, the screw pins. So we got to make sure it has all these appropriate things on it. If it doesn't, we should be in doubt. There are cheap knockoffs running around out there that don't have information or they have misinformation on them. Everything we have should be brand name. So you're going to look for your name or trademark, the capacity, the size, and the pin identification. It's important the pin identification should match the shackle. These things come in sets. If your boss ever hands you a crate of pins and shackles and says match these up or just make these work, it's not really right. We want the pin to have been through the same shit as the rest of the shackle. We don't want to be grabbing pins that have been dealing with heat and putting them in shackles that have been dealing with acid. It makes for a bad combination. We want the whole thing to be treated as one unit and not just pieced together. Be aware of load-bearing components that are bent, twisted, distorted, stretched, elongated, cracked, broken, and we're going to see this list over and over and over again. Those are all the things we want to be mindful of. Obviously, this one's got a pretty evident crack. I mean, just the look of it is cause for concern. And if you take that concern and give it a good visual, you're going to find that crack. It just looks rusty and used and worn. Excessive nicks or gouges, 10% reduction of the original catalog dimension at any point around the body or pin. So if the thing is 1 inch, you get a tenth of an inch. I'm not going to do math on that, but you get 10% loss of whatever dimension you're measuring is copacetic, is okay. So if this thing is 1 inch, you can lose 1/10 of it. That's probably too much. But the fact that there's multiples is the biggest problem. You might be able to get away with 1 piece of damage, but if you have 10 pieces of damage, well, that's just great fun. Any other condition, again, which causes doubt. So if you see something you don't like, stop and ask. Most of our stuff should be in decent shape, but things happen. Screw pin must be tightly and fully engaged with the shoulder and in contact with the shackle body. So, rule of thumb, just tighten it. I was taught multiple ways of doing this. Some guys say, put a pin bar in it and crank down on it. Some guys swear you're supposed to back it off a little bit so you can get it out easy when you're done. No, it's just tighten it in there until it stops. And when it stops, you shouldn't have any thread showing, and this should be shouldered right against the shackle. If it doesn't, there's probably a stretch or a compression thing going on there. Just be mindful of that. But yeah, you don't have to do anything creative. If it's properly tightened down, just snug it down by hand. You don't have to get a tool and reef on it harder. It's not going to do any good. It's actually going to do more harm than good. Never replace a shackle pin with the bolt. The load will bend. The bolts are not load rated. They're not designed to be used like this. They're not heat treated. You can't just replace one with the other. If you're going to use a bolt for rigging, use the bolt. Okay. Never use a bolt for rigging. It's wrong. We've never done that here ever. I swear. No. We used to lift chuck plates with a bolt. Just put a bolt through the hole and put slings on the bolt and lift it up. Bad. That was in my first.
We did too.
It's been done. It's not the right way to do it, and that's because bolts are not load rated for that type of load. Use the right tool. We've gotten a lot better with buying the right tools. Most of the time we're using the swivel eyes for chuck plates now, which is the right tool for the job. Be mindful of aligning things in the direction of loading with no interference. Corner interference with shackle laments. That's a good way to bend your shackle. Plus, you can't really tell if your shackle's rated properly because all the load is now in here, and you're going to run the risk of bending your shackle, damaging your load. It's just that's not the way it's supposed to work. Center the load in the bow of the shackle, so you don't want to capsize like what you see on the left there, where things are all cockeyed and askew. If need be, you can put some washers in there to hold things straight so it all picks up nicely. But you also want to be mindful that you're not putting something too small in there where all the load is on one tiny little part of it. So I hate to say use common sense, but if you don't know, ask. And if it doesn't look right, it probably isn't. Don't apply multiple slings to the shackle pin. Typically the pin should be in the hook or in the eye bolt or whatever, and then the slings are going to go through the loop. It's not supposed to go on the pin. There's a chance it could cause the pin to roll out. And plus, in this case, they're stacked over top of each other, which isn't ideal. So when you're side loading a shackle, the rated load must be reduced. And this is common. We've had to do this around here, but the thing we need to consider is just how much we're derating it. So you're losing half the capacity of your shackle when you're doing what we see there. So that's pretty drastic. Screw pin must not be rigged in a manner that will cause the pin to unscrew. So in this case, they've got the bail through the hook, and then the object can teeter-totter back and forth on the pin. I mean, that's just bad rigging to begin with, to loop your sling through there like that. But people have done it, so. Multiple sling legs in the body of the shackle must not exceed 120 degrees of the included angle. So, yeah, and the reason for that is if you go much more than that, you're going to basically be pulling that shackle apart. All the strain is trying to fight against that shackle and open it up. And if you were to have these at a more extreme angle, even if they would stay put, you'd run the risk of bending that shackle and stretching it. Plus your masses on your load or your tension starts to get pretty insane. So for eye bolts, there's the three different kinds: your machinery eye bolt, your shoulder nut eye bolt, and a non-shoulder nut eye bolt. Make sure they have their names and trademarks with the size of rated load and the grade. What type of damage? In this case, we got a slight bend to it, so it's probably been misused and caused the bend. So it's pulled at an angle and not shouldered to the load. So again, if it has a shoulder, it has to be shouldered, at least for these machine style ones. This is a good example of why you are responsible for the thing that you're lifting. To the untrained eye, that seems okay. I mean, it seems to be supporting that zip tie just fine. But the hole next to it is a good example of why the hole that's being employed is probably not a very good hole to use. And upon further inspection, so you got a countersink going on there, not to mention the fact that it's almost cut the threads off. So that whole thing was probably being held in by one whole thread. So it would not have held the mass of that object when you lifted it up. So do your diligence, make sure you know where you're attaching things, not to mention it's incredibly close to the very edge, which is bizarre, but maybe the manufacturing plant used it for one of their operations. It was obviously there when the whole thing was powder coated, so it might have been part of their process, but it's not good for us to use. Capacity is effectively zero. We have no way to know what that thing's rated for. That is not a pick point. So when you're using a shouldered eye bolt, you need to make sure that it's tightly secured against the load and the full threads are engaged. If you are doing an angular lift, you may use one flat washer under the shoulder to position the plane of the eye. So what this allows you to do is to get the eye bolt in the right orientation that you need it to be in by adjusting it against the washer, but you'd never use multiple washers because that'll just effectively make it unrated too, because it can still bend. Only shouldered eye bolts can be used for angular lifting because they have that shoulder to spread that load out. Eye bolts must be shouldered to the load. So in this case, you've got a nut with it's got a shoulder, but the shoulder's not against the load. So you can use this for a straight pick, but you cannot use it for an angle pick. It's just going to fold right over. You would want to have this all the way through the nut on the back and the shoulder against the object to make that proper use for an angle pull. Otherwise, it's only good for the straight pull. With an untapped through hole, so just a random hole cut through, whether it's drilled or torch cut or whatever, it shouldn't be torch cut because torch cutting the heat will screw up the metal and affect the molecular composition and make it fragile. But if you have an untapped through hole, you must have it shouldered to the load, and then you have a backing nut fully engaged behind it to secure it in place if you don't have all the threads engaged. When using shouldered eye bolts for angular lifts, the plane of the eye must be aligned with the direction of loading. So you want this thing rotated so that link or the hook can align itself and pull in the same direction. In this case, it's going to capsize like that. Even if you had the hook directly through it, it's still, the force is going this way, and it's going to want to just bend that thing right over. Never insert hook tips directly into the eye bolts. Use a shackle to prevent binding. So yeah, obviously if you're doing what's on the right there, you're going to run the risk of point loading it and breaking the tip or bending the tip. Put a shackle in first, put the pin through the eye bolt, and then the hook through the shackle. This shows us just how drastic side loading eye bolts is. Not so bad, we lose 25%, but it can get, it's much like our shackles, they lose half. You start mixing these problems, you basically have next to no capacity left. So for a straight pull, you get, your 100%. When you start just moving it that little tiny bit, we're getting 55%. And sorry, I misspoke. This is actually horrible. At straight pull, you're getting up to 100%, down to 90% for that little angle. For just a little extra bit, you get down to 55% of your rating. And if you go 90 degrees, you actually only get 25%, which is shitty. So it's insane. If you have an 8-ton eye bolt, now you've got 2-ton capacity. So it's amazing what an impact angles have on your equipment. Whereas a straight pull, you're laughing, you're good to go for 100% capacity. Now these things are the bomb. If you can get your hands on them, we do have them. They're also considerably more expensive, but they are the best way to go because you can use it in any, it stays the same regardless of what orientation, it self-aligns. So unlike this situation where you have to worry about getting it in the right orientation, possibly by using one washer, this one, it'll just put itself in the right orientation because that's how it's designed, and you don't lose any capacity like this. When it folds over and goes 90 degrees, it's still full capacity. The one operative thing with these is they're not rated until they're torqued. So don't just crank it in with as much muscle power as you can muster. You have to torque it to spec. Most of us have probably done that. But if you're over-torquing it, you're doing as much harm as you're stressing those threads out by over-torquing it. If you're under-torquing it, it's pretty self-explanatory. You want to make sure you actually dial these in with a torque wrench to get your maximum value. So your working load limit's only 2,500 pounds if you torque it to 28 foot-pounds. And again, these things can be repaired. You can replace just about every single part of these things if it is damaged, and that's a saving grace. It's more expensive, but it also is repairing. The top pushing flange must be in contact with the load. You don't need spacers or washers because it swivels under its own power, and it will self-align to where it needs to be. Make sure that it is fully torqued and it's free to rotate and pivot without interference. So in this case, the interference is the object that's now binding against. You've got a point of contact here. You'd be better off if this was on the top. It could turn and swivel freely, but since it's on the side here, it's binding up against the edge of that plate, and that's going to run the risk of damaging it, and it screws up your capacity in a way that you can't really quantify. It isn't good, and if anything, you're going to damage that expensive tool. Now, hooks must be narrower than the inside width of the bail to avoid spreading. Pretty self-explanatory. Don't jam a massive hook in a small hole. If you want to put big things in small holes, do it somewhere else. Don't do it here, and don't point load, just tip. Oblong master links with sub-link assembly, and then a pear-shaped link. Reminds me of an episode of Bundy's. Master link capabilities and maximum loading angles must be in accordance with manufacturer's specs. Consult your manufacturer capacities and maximum angles. Turnbuckles, again, not something we use here for rigging. We do use them in our equipment, but we don't really use them for rigging. They can be handy because you can adjust the leg length when the thing is under load. You can put wrenches on it and turn it when it's under tension, which is something you can't do with anything else, so you can actually kind of live adjust it. So in this case, they allow you to dial in if you needed to get that frame in perfectly and just right, just level, and you could actually use the turnbuckles to adjust it while it's in the air. Or under tension anyway. They must be rated for lifting. They allow inline loading only, adjusted on wrench flats of the body only, and lifting threads shall be fully engaged and verified before the lift, and they may be adjusted under load, and that's probably their most useful point. Different styles of hooks. We have sling hooks with self-locking, grab hooks, boundary hooks, and sorting hooks. Typically ours are going to be the sling hooks or the self-locking sling hooks. We do have, I think, a few grab hooks we use for moving a cans and assembly. If you find yourself using any of these ones, especially these two, make sure you know how to use them, and we will touch base on that in this course. The other two are pretty self-explanatory. They latch shut and hold the objects inside them. Shank connections, a shank hook with self-locking gate, and then there's swivel connections, a swing hook and a sling hook self-locking. The hook must be used in a manner for which it is not intended, so don't just snap it in the hole of the battery and use it to lift the battery. Batteries have specific lifting devices made for them. If need be, use shackles or whatever else. Don't just assume that the tip fits in and you can use it. Again, if you're in doubt, ask. I know this is a test question. The maximum included angle of a hook is 90-degree total. That is a test question right there. So sometimes you'll see the 245s indicated on the object or on the hook. Your total included angle is 90 degrees if you have everything laying where it's supposed to be. But that's just to avoid stretching the hook. Otherwise, if you had them farther out and were pulling straight out to the sides, well, it's going to bend the hook, break the tip, whatever. Use a shackle when 2 or more sling legs are placed in a hook. So if you do have a bunch of slings, use a shackle. I was taught you're only allowed to put 3 things in a shackle. This says 4, it says more than 2, but that's only for the direct hook. I wouldn't necessarily put 4 things in one shackle. I would probably put master links or something else in there and go back to them, or more shackles for that matter. Either way, you just want to avoid putting too many things in. They move around. In this case, you're going to run the risk of tip loading on these ones. Again, if it looks wrong, it probably is. Hooks must not be used in such a manner as to place a side load, back load, or tip load on the hook. So the side load on the left, the tip load on the right, and the back load in the middle. You're binding the hook against another object you're lifting. That's no bueno. Orientations of the hook. So again, this is why you put your hooks out, not in. And this is a perfect example of why, if you're using the chain to actually wrap around and choke it, you don't want to have it on the inside, because that chain is trying to go towards the middle and it can actually slip out. Whereas if you spin that hook around, the chain's now binding against the back of the hook and not trying to pull itself out of the hook. So always make sure your hooks are placed hook tip out. Sorting hooks, they must be engaged to full depth of the hook throat. Don't concentrate the load in the last 2 inches. I mean, the one on the right is definitely wrong for all kinds of reasons. But these things rely on the tension they create when lifting to hold them in position. So you actually have to have an angle where your sling's going to come out this way. If you had your sling straight up and down, it's going to want to rock. You'll be tip loading, and it can very well fall out. They'll show us some more pictures later. But you actually need to have that tension inward to hold that thing in position, as shown here. So you have to maintain that 30 to 45 degrees. Once you start going above 45 degrees, and heaven forbid you went up to like straight up and down, there's going to be nothing pulling this thing into the load, and it can very well slip out and fall. Below the hook lifting devices. So these things are all very unique. Plate clamps and magnets are interesting, and I think the only person who uses them a lot is going to be Clark. I know assembly uses magnets from time to time. Don't think you guys use any plate clamps whatsoever, really, because everything you're working on is finished goods, and you would not want to put a plate clamp on powder coat. That would be a shitty idea. We don't cause a lot of cause to use spreader beams. We do have them, but we don't find use for them around here very often. I like to say that the plate clamps and the magnets use magic, because you can't see how they work. They're using magnetic fields, so you have to be very careful with them. Plate clamps, they use pressure and friction. Same thing though. The 2 biggest things I like to point out, and we'll get into this more, is these 2 things have minimums and maximums. Nothing else does. Both of them have minimum thicknesses, minimum masses. nobody's going to tell you you can't put 5 pounds on a sling. A sling will pick up 5 pounds. You put 5 pounds on a magnet, it probably won't even hold it, or worse yet, a plate clamp, there just won't be enough friction there for it to bind. So when you're using, if you find yourself using plate clamps and magnets, make sure you get to know the plate clamps and magnets you're using and their capacities, what they're made for. There's more things to consider with plate clamps that we'll get into, but there's a lot more to them than your average sling. When you choke something with a sling, that son of a bitch is going up. Doesn't matter what you're doing, it's going to lift. With a magnet, there's no guarantee it's going to lift. With a plate clamp, it might lift far enough to fall on your foot. And that they can be quite scary, and you just have to really get to know them. If you've never used a magnet or a plate clamp, make sure you ask before you do. You won't find yourself using these really at all in assembly, but you may very well wind up using one of those. And you do just need to stop and ask, because they can get you to where you think you're safe, and then things just fall. And there's nothing to stop them like a sling. So I can't stress that enough to a new user especially. You really have to consider that stuff. The lifter should be applied to the load in accordance with the manufacturer's recommended operating procedures, and the lifter should not be used for loads which it is not designed. And that's a big one when it comes to magnets and clamps. Lifters should not be loaded in excess of its rated load, and they should not be accelerated and decelerated smoothly, or they should be accelerated and decelerated smoothly. Same thing. Shock loading a magnet, the thing will just fall on the floor. Shock loading a clamp, same thing can happen. Whereas a sling, it might bounce, especially if it's a minimal shock load. So plate clamps, there's a lot of things to consider when you're using these things. You don't have to remember all this information. Just know that there's a lot of variations. They're very particular tools designed for very particular applications, and they're not all created equal. One plate clamp is not the same as the next plate clamp. So make sure you're using the right plate clamp for the application you are being asked to do. One thing to consider as well with plate clamps is the only time you're going to see hardness is an issue. Because if it's too hard or too soft, if it's too hard, it won't bite. If it's too soft, it'll rip it apart. And if it isn't the right material, it'll cross-contaminate and get your boss yelling at you for causing rust on the stainless. So you really got to make sure you have the right one, and you know the material, and you know the clamp. If you're in doubt, these are the one time I'll advocate, get the instructions and read them. It can really save your butt if you don't know what you're looking at. In this case, a vertical lifting clamp, steel plates and sections up to a surface hardness of 300 Bernal. It can lift and turn over plates or transport in the vertical position. And for long plates, use a beam with vertical slings in each end. So you'd want to use a spreader bar basically. But again, there's like 5 of these slides. You're not going to remember every one of them. Just get to know the plate clamps you have and how they're supposed to be used. So this one doesn't have an articulation here. So it's designed to only use in one orientation, kind of. This one has the articulation, kind of like those swivel eyes. It's designed to bend, so you can. But you still, the other thing is you have to maintain a load on these things. If the load is removed for any reason, stuff just falls off. Same thing up to a surface hardness of 300 Bernal. So again, the reason for that is if the surface hardness is more than 300 Bernal, the clamp will not actually bite down on what it's lifting up on, and it can fall out. Lift and turnover plates, 180 degrees or transport in vertical position, can be used in pairs with sling angles. So this one, instead of this one, you have to use a spreader bar. It says to use a bead with vertical slings. This one, you could use angles because it has that articulation. This one has an articulation, but it's for stainless, and you can tell it's for stainless because it has stainless steel components, so it won't cross-contaminate the carbon with the stainless. For stainless steel plates and sections, they can lift and turn over plates at 180 degrees for transport. The pivot in the can segment is made of stainless steel to avoid contact corrosion, and they can be used in pairs with sling angles. Again, the angles are indicative of the fact that it's got that articulated bend in it. For structural plates, including aluminum, stainless steel, and steel with a surface hardness greater than 300 Bernal, avoid oily surfaces, and that's a huge thing too. The surface condition plays a massive role in these things. If you've got mill scale, oil, anything else, it's not gonna, the friction won't exist that it requires. It needs the friction of the plate, these binding together against the surface, and if it doesn't achieve that, it's gonna just fall out. And it'll usually fall out after you get it off the ground. It'll work just long enough to get dangerous, and then it'll fall. You won't be lucky enough to have it slip off on the ground. It'll slip off in the air. Or when you stop the crane suddenly to stop getting Bob while he goes to lunch, and then the thing falls on your foot and ruins your day. For long plates, use a beam with vertical slings on each end connected with each clamp. again, I don't expect you to remember all this. It's not on the test. These are, if you're using these things or you go somewhere else and you're using these things, make sure you're using the right one. Ask to see the instructions. Don't just take their word for it. It's the right one. Oh, we have one clamp. We use it for everything. No, definitely no. Short beams may be lifted with a single clamp, so these ones are pretty wide. And for a short beam, you can get away with using one of them. Otherwise, you're going to use them in pairs with the vertical with the spreader bar. Girder beam clamps, so this one you can use for moving and stacking beams when they're in the H position. Again, if you're an iron worker, you'll get to know these things intimately, I'm sure. Long plates use a beam with vertical slings on each end. Sorting and transporting horizontal positions, non-sagging materials or bundles. So that's a huge thing there, is non-sagging. If what you're lifting is flexible, like a sheet of steel, you need to consider that. I mean, anytime you're rigging, you need to consider how bendy the thing you're lifting is. I've seen people take 100-foot sections of pipe and have them fold over in the middle and make we call them the golden arches, but it just made for a big U shape because they didn't support it properly. Same thing with plate. If you pick up a plate that's bendy, it'll get off the ground, then it'll buckle, and it'll just slide right out of your clamps and hit the ground. They must be used in pairs, so one on either side. If anybody ever hands you something like that, don't use it. Again, it looks like they picked it up off the ocean floor. It's definitely been seen better days. Things to consider. So this is, the weight of the load is, it's not just the minimum, it's also the maximum. Or sorry, it's not just the maximum, it's also the minimum. There is minimums. The hardness of the load, the type of material, the position of the load, and can the load be marked. So you don't want to pick up something that needs to be maintained looking perfect with a clamp that's going to put teeth marks on it. Again, that's why we don't use them all that much around here. You guys probably, do you use clamps much in welding? Probably not a lot, because they would damage the surface, right?
We do.
You do for certain things.
And like some of the metal has like red, it's like reddish.
Yeah.
And it's slippery. So
Okay.
before you lift, you give it a yank.
To kind of fight it in there.
Yeah, like sometimes
that's
you'll
fair.
notice right away if it's going to slip.
Well, that's fair.
It's bad.
That's not ideal, though. I mean,
So then, like for Lance, it was slipping a lot, so he would have to like grind and give it some something to grab on.
So that must be only specific things, because obviously if it's a finished weldment, you're probably not grinding a dent into it or.
Yeah, no, not
teeth
again.
marks.
Just
Yeah.
taking the mill scale off. 'Cause
Yeah.
Some of it's super slippery.
And the mill scale is a huge thing. Like the surface condition matters a lot when it comes to these things, because it just can't bite properly. Or worse yet, it bites the mill scale flakes off, and the whole thing slips down.
Yeah.
So yeah, the clamps are something you really need to be careful with if you're using them. This is your kind of standard clamp you're going to see right here. Make sure it's got the manufacturer. And again, these ones you really want to make sure the information's on there because it does matter. Serial numbers, the clamp weight. Anytime you're using rigging and the rigging itself weighs 100 pounds or more, the weight of the rigging will be on there. And that's because if you're doing rigging operations where you've got hundreds of pounds of rigging, you need to consider that when you're considering your capacities. So the maximum rated load and the minimum rated load. And this is the big thing. These have a minimum load. So you've got to make, like, it's got a 0.1 of a ton to 1 ton. So you cannot lift something that's under 0.1 of a ton, which is what, 200 pounds, because it will not provide enough downward force to bite against these teeth. It'll just fall right out, nice and limp. And likewise, it has a maximum minimum thickness as well. You cannot put something in here that's too thin because it will not properly bite against these teeth. Like too wide, obviously won't fit. But if you go too narrow, it won't properly grab. And if it doesn't have the right mass, it won't properly grab either. So a lot more things to consider. And for your basic rigging, again, there's no minimum for a sling. A sling doesn't care what you're lifting. It'll just lift it. But these things definitely do. So you have the lifting eye, the body itself, the pivot, the cam, the spring and locking lever. Saving grace with these things is they can be maintained. I've got one in my office, played Rob the other day actually. It needs to go out for service, no big deal. These can all be replaced and fixed. We can maintain it to keep it going. So things to consider for removing these from service: look for any deformation, cracks, or wear, loose or missing fasteners, nameplates, etc. Unauthorized modifications. Yeah, if somebody welded something to your clamp, don't use that clamp. Improper assembly or function, seized moving parts, gripping teeth, worn, chipped, clogged, missing or unreadable labels. This is probably going to be one of the most common things you see is the worn teeth. So if these start being chipped or broken, you're not going to, what can often happen is if the clamp gets used over and over and over and over again for the same thickness of material, it's going to wear in the same place. So it's going to take shit of use and start losing teeth in that same place. That's fine, but you just need to be mindful of it because it cannot now bite the way it's designed to. And here's just some not great pictures of what you want to look out for. Basically, if you find anything in there that you don't like, talk to someone. If none of us are really experts at this, we can always send out and have the professionals look at it and replace the parts. This one's a little more obvious. You've got some damaged teeth there. They're chipped. So make sure you read the manufacturer's instructions. And honestly, for just about everything else, I'm not worried about instructions. It's like maths, cheating. But if you find yourself using clamps and even magnets, but especially clamps, read the instructions if you don't know, because there's so many variations on a theme, and they're all made for different things. Again, you have to consider the hardness, you have to consider the mass, you have to consider the minimum mass, the thickness. There's just and then which angle it's going to work at. And again, the biggest problem is it'll work until you get that thing in the air, and then it'll fail. It'll never just fail on the ground. That'd be too easy. So yeah, always apply the minimum load. And this is I cannot stress this enough. The simple fact that a minimum load exists is kind of counterintuitive to rigging in general, but it's actually a thing with clamps. So always know that you're applying, because otherwise that downward pull just won't be enough to properly engage those teeth. Use 2 or more lifting clamps to balance longer flexible loads for obvious reasons. And again, this is the right application because it's got that articulation, so it allows for the sling angles. If these didn't have the articulation, you'd want to have a spreader bar with 2 different slings going down, or 1 to each one. The equalizer beam should be used when more than 2 clamps are in use, so that just spreads the load and makes sure that the slings are straight up and down. And then, yeah, we also need to make sure that the type of material we're lifting, ensure compatibility with the material. Don't use carbon steel clamps on stainless steel or vice versa. It's not going to bite. That whole hardness thing comes into effect. What are the possible reasons the clamp's not gripping? We may have the plate might be too heavy, which it just will not work. The plate is too light, too hard, not clean, or its pivot or the pivot teeth are worn. Teeth and pivot are worn out. So there's just a lot of moving parts, literally, to be mindful of, and it's really easy to do it wrong if you don't know what you're doing. Another obvious problem that might not seem obvious unless you know is don't lift more than one thing at a time. It relies on that pressure between the back of this plate and those teeth to maintain the bite. Obviously this one at the back, now you're just praying it's going to stay there. It's probably going to slide out, and again, it won't slide out until you get it off the ground. Then it'll fall over and make a mess and a loud bang, and hopefully it won't kill anyone. So only one piece at a time. Same goes for magnets, they'll show us that as well. And then also there's the minimum and maximum thickness of what this thing will lift. And I don't think the maximum is dictated by the dimension here, because you need to make sure that that this thing can actually bite against it. So you'll have to look at the information on it and make sure you're using it for the thickness it is designed for. If you don't, it either will bite just enough or it won't bite at all. Either way, it's not going to work out in your favor. Never stand beside a suspended plate. The danger zone is considered to be 2 times the height of the plate, and that's because it can fall, deflect, tip over, slide, whatever. Avoid sudden acceleration, deceleration. Again, shock loading with a sling, a little bit here and there. Obviously, it's not ideal, but you're probably going to get away with it. Shock loading with one of these things or a magnet, a whole other story. It'll just rip the teeth off. It'll just rip the piece out of the teeth. It's really hard to quantify exactly the effects a shock load is going to have when you're floating a plate across the shop. So you really need to be mindful of how slow or fast you're going and avoid any sudden stops or starts. And you cannot contact any obstruction, because these things work by maintaining that downward force of the weight of the object. So if you're flying something across this room and you rest one corner on the table and go for lunch, well, now there's no mass pulling down on that one clamp, and it could pop off and the whole thing falls over because you left it there with no load on it. So, like I say, unlike a sling, these things are very particular, and you just have to be cautious and use them correctly. Another example, there's that whole flexible load thing. These plates or these clamps are designed for that pull. Just like a sorting hook, it needs that pull inward to maintain. And if it starts doing this, it's just going to fold and slide right out and fall. And again, it probably won't happen until you're already off the ground. So always, and not to mention the potential damage to the product itself. So you just always have to be mindful of the rigidity of what you're lifting up with this stuff. Same goes for magnets. We'll see that in a bit. Hoist lines must be kept vertical when lifting from horizontal to vertical or when laying a plate down. So if you've never rotated an object, you're not going to learn how to do it in this class. Really, the only way to get good at this stuff is doing it, and you're going to have to work with someone who has done it a lot. A lot of you guys in assembly roll a lot of things over and you get pretty good at it. Vitaly, I would not want to see you rolling anything over tomorrow or the next day. You're going to have to get with someone who knows, who's done this more. And this isn't really it, but this is the same approach. You need to maintain your lines on your crane vertical at all times and not just set it on the ground and lay it down and leave your crane over here so your lines are all sideways. Again, because that's going to release that tension on the clamp. So, and it's bad for the crane too. So you just want to maintain everything straight up and down. Don't leave the load resting on the floor in the vertical position. There's no load in the clamp. So when you come down to hit the floor, keep going until it starts leaning over. If you leave it just sitting on the floor and go for lunch, it's effectively just hoping it stays inside that clamp, because now there's no mass pulling down on the clamp, and it's going to release those teeth and potentially fall. So again, the lifting clamp must not be loaded above its rated capacity or handle any load for which it is not designed. Yeah, don't apply the 5-to-1. Oh, I've got 5 times safety factor. Not with a clamp. You don't get that. It's not like a sling. A little extra is not going to hurt. No. Don't ask for miracles from these things. Use them within the guidelines they're designed for, because there's very little physical contact keeping you from disaster when it comes to this stuff. Don't use vertical lifting clamps for horizontal transfer materials unless it's approved by the manufacturer. So make sure you know the clamps that you're using. These ones have to have that pull to maintain that bite. It's the articulated motion here. This pulls up, this bites harder. That's what you need. If you remove that, it's not going to have that tension and it's going to just pop out. Magnets. Again, I make the joke they rely on magic. And I say they rely on magic because you literally can't see what the hell's going on and you're just hoping it's not going to fall on your feet. A lot of people will say magnets cannot be used on round things. Sure they can. It's derated. It does say on the tag if it's good for round objects. But because it's minimal surface contact, it doesn't necessarily have the same capacity. But yes, you were basically praying that magic force holds that thing in position. If you stop suddenly, it can peel off. If it bends, it can peel off. Same thing. There's maximums, minimums. There's minimum thicknesses, all that kind of stuff you have to worry about. When using a permanent magnet, use a permanent magnet to maintain holding power. The only way they're made. They're for lifting flat or round steel. They're activated when the lever is rotated to on, and they're deactivated when the lever is rotated to off. And that just brings the magnet into contact with the base plate and activates the magnetic field into the object, kind of thing. It's not literally an on switch unless it's an electromagnet like a mag drill. Same kind of stuff you want to look out for. Make sure there's a manufacturer's name and contact info, a serial number, the weight of the object itself. If it weighs over 100 pounds, again, that's because if you're doing a massive lift, you may have 1,000 pounds of rigging, and now you need a bigger crane. And then all the engineering stuff it has to match. So again, this is where all the surface condition, the type of material, the heat. I mean, if things are hot, they lose their magnetic characteristics. A good way to tell if your metal's hot enough to weld is heat it until a magnet won't stick to it. It's like the most generic way to know in the field if you've preheated your steel enough, is just heat it until you can't stick a magnet to it, and then you can go ahead and weld. If you don't have a temp stick handy or something, it's a good trick. But the surface condition, in this case, you've got a ribbed surface or it's striations on a flange or whatever it might be. You need to be mindful of that. You have to make sure the bottom of your magnet is clean. So you want to look for air gaps caused by dirt, burrs, rust, scale, frost, moisture. That'll all affect lifting capacity. Yeah, if you're lifting up something that's cold that just came in from outside, there's a layer of moisture on it, it's going to be inherently slippery. It can slide right off the magnet. If it's got a mill scale on it, if it's too hot, it might not be magnetic or properly magnetic. Any dirt, any random shit that gets caught in there. The thickness of the load, in the case of a magnet, the thickness matters a lot. You can lift something thin, but it's probably gonna, again, it'll lift high enough to then fall, especially if you lift it high enough and then stop suddenly, or bring it down and stop suddenly, it'll just fall right off. And that's because those magnetic field lines aren't all in contact with the object. So you're better off with this thick one where it's using the entire magnetic force available and not just half of them. So again, there is a minimum maximum thickness, or definitely a minimum, not so much a maximum thickness when it comes to magnets. The entire magnet must make contact with the load and lifting capacity is reduced. So because it's not that it can't lift a round piece of pipe or whatever it might be, or a round bar, but it's going to reduce the capacity because the entire magnet is not in contact. That being said, most magnets have a groove in them to allow things like that to fit. Flexible loads, again, they can peel off the magnet, so you either need to use multiple magnets or something different, because the stress caused by all this mass folding down can literally just overload the magnet. It'll just peel right off and fall to the ground. Higher temperatures, the higher temperature, the more resistant to an applied magnetic field. You can literally heat metal up to the point where it's no longer magnetic, so that matters if you're working in a shop with heat, as the welders do. Or if you're working on something that's being tested over an assembly, or Tony's doing weld testing or something, don't just slap a magnet on it and lift it up. Or a sling for that matter, you'll melt the sling. Much like the clamps, they're designed to lift one piece at a time. Problem you're going to have there is, again, you might be able to get it off the ground, and then all of a sudden you have to stop, and that bottom piece falls off, or worse yet, both pieces fall off. So only lift one piece at a time. You're not being faster by doing two. Same thing with these. Every part can be replaced and serviced. You get the lifting bail, the control handle, the hardware, the labels and the marking, and the safety lock. Check the magnet's face for foreign materials and smoothness, so you're making sure you're getting maximum contact. If it's got a bunch of stuff on it, or the surface does, it's not going to sit flat. Do not load in excess of the rated load or handle any load for which it's not designed. Use in accordance with the operator's manual. Center the magnet on the load. Yeah, I mean, if it's not centered and it's capsized, now you're putting unequal force on it. And again, it could slide off there. And it's not that it'll slide off right away. It'll slide off when you stop because that forklift dart's out in front of you, and then it's going to fall. And don't use for side pulls for obvious reasons, because it could slide along the surface or just release. Temperature limits, both ambient and contact. Again, around here it's going to be hot stuff from welding usually, or cold stuff from bringing it in from outside. Avoid swinging, because any amount of swing can impart a shock load, and these don't have that 5-to-1 safety factor like a sling does. There is no safety factor. If it says it's good for 1,000 pounds, I wouldn't want to inadvertently put 1,500 pounds on it because you side load it, or because you shock load it moving it back and forth. So just be really, really mindful if you're using these things to use them with the respect they deserve. Don't allow the load or lifter to contact any obstruction. Same idea as the plate clamps. You don't want to bump. Worse with a magnet, if you were floating something across the shop and you bump into something, well, now that shear force could just pop right off the magnet and then have it fall off. So you just need to be super cognizant of how you're using these things. Operator must only lift the load a few inches to check the load is securely attached. This is good for clamps or magnets, where that kind of a test lift is always good. Lift it up off the ground, have a look. Is it sitting level? Is it holding well? Everything looks good. And only lift it as high as you need to. Don't fly overhead if you don't need to. It should never be over your head or anyone else's. But if you don't need to take it 20 feet in the air, don't. I always recommend for everything lifting related, bring it up to this height, whatever that is for you. So for me, it's 3 feet. For Dave, it's 4. It's all right. But this is a nice, comfortable height. You shouldn't be leaning over and walking along doing this. You should be comfortable, and then you're not. The worst thing that could happen is it falls on your feet, which is why we wear steel toes. Not that that's going to help necessarily, but avoid lifting things higher than you need to, especially if you're using magnets and clamps. Spreader beams and lifting beams distribute the weight of the load across more than one point. They remove compressive and crushing forces caused by sling angles. So yeah, as we're going to learn, sling angles create compressive forces. Everything's trying to pull towards the center. This eliminates that. Everything stays vertical, stays nice and comfy and happy. Absorbs the crushing force of angular loading. It converts angular loading to vertical loading at the load's pick points. Converts lifting load into bending moment through the beam and reduces headroom requirements. So if you do have something where headroom is an issue, they can be advantageous. Make sure you have the manufacturer's name and contact info, the serial number, the weight of the object if it's over 100 pounds, and the ASME codes. Removal criteria: look for deformation, cracks, or excessive wear. Excessive wear, hoist hooking points and load support shackles or pins. Loose or missing guards, fasteners, covers, stops, or nameplates. The loading on the top slings becomes unequal. So yeah, we want to avoid using these for unequal loads if we're not using them properly. Basically, the spreader bar should always be level. Really good spreader bars, you can actually move the lifting points, or they have multiple lifting points to attach to. The rudimentary simple ones just have 2 hooks that spread the load out. Make sure it's right for the application you're using it for. You might be better off to use slings and choke them, bring it back to 1 hook. Just all depends. For non-symmetrical loads, adjust the lifting bail towards the center of gravity so the load will lift level. Ideally, we want to lift everything level. That being said, not everything has to lift level. It depends what you're doing. If you're just picking a unit up and dragging it across the floor, you don't have to pick it up level. If you're trying to install something, level probably matters. Equalizer beams provide load equalization in each sling leg. And yes, there's situations where you're going to use multiple, where they actually rig up more than 1 equalizer beam. Unlikely. We're definitely not going to do that around here, but it can be done. Lever hoists, chain falls, come-alongs, all the different parts of those. The main thing we need to know is if we're using a come-along for lifting, it has to have a brake. Because if the mechanism breaks, we don't want it to freewheel and fall. We want it to stay where you put it and not just string out and hit the ground. So you make sure that the chain fall chain falls are inherently made for lifting. Come-alongs are not all made for lifting, so make sure you have one that has that hoist brake in it. So if the mechanism fails, the thing doesn't just fall out and hit the ground. Inspect the operating mechanisms, the hoist latches, the load chain, the over travel restraint, the hoist brake, and the hoist body and lever. Connection points for anchoring means must have sufficient capacity. Operator must be clear of the load. The operator must have firm footing. The operator must have adequate access to the operating lever. Operate the hand power at the operator only, and don't use extensions on the lever. So don't put a snipe on this thing and crank on it harder. You want to take a quick break and walk around, Dave, you're just falling asleep. But I don't blame you. My monotonous or my monotone voice will do that.
No,
I know it's hard.
No, I slept like shit last night.
It's all good, man. Everybody is.
I apologize.
No, I'm not calling you out. Honestly, if you want to get up and take 5 minutes and just go for a stroll, you don't smoke anymore, do you?
I do.
You want to go for a dart?
No.
Okay, fine.
I appreciate it though. No, I don't.
At least bathroom.
Yeah, take a break. If everybody wants to stand up and stretch the legs, take a pee break. It's only 10, 20. You've got lots of time.
There's still coffee on the other side?
Oh yeah. Well, I mean, whether there's coffee there or you can make one.
Interrupt you that
Oh,
you
it's
can
all
choke, right?
Oh yeah. All like the chains we have on our crane, you can use those as chokers.
Okay.
Like the chain slings, you can wrap around stuff.
Our
Yeah.
15,000 loads you
Yeah.
could
Wrap right around
which
itself.
you only have
As
one.
long as you mind your sharp edges, your like all that stuff we learned
Right,
earlier, the
angle around it.
radiuses and all that, you can totally do it.
Oh.
Kelsey's notorious for doing it because his new old, I'm going to say welder in him, despite him not being a welder.
Yeah.
I don't think that's one of his tickets. But he's just hardwired, just grab it, wrap it around it, and go. Most of us put slings in the middle. And again, for some things, you can totally do it, but then you need to consider the damage that you're going to cause by doing it potentially, especially in assembly. These things have been done wrong a million times. I mean, I've used these wrong a million times in my life. There's all the wrong ways to do it, and only really one right way to do it, which is a straight, nice pull. But again, make sure you're using one that has the brake mechanism in it so it can't fail and just fall to the ground. Several ways to determine the load weight, shipping documents. Now we're going to get into some serious math that I don't want you guys to like freak out about as we start to determine how to calculate load weights and awkward loads. This course used to just be basic rigging. Now they've amalgamated it with the advanced rigging. It's useful information, but don't freak out about it. If you're not comfortable with this stuff, just don't do it without getting someone else to help you. That's my precursor to what we're going to get into. There are several ways to determine load weight. You can use shipping documents. Bill of lading should have a pretty accurate weight on it. I would say blueprints are usually good. Around here, they're touch and go just because it says on the print what it weighs. It may or may not be very accurate. We might design these things from the ground up ourselves, but for some reason, we're not very good at getting the weights consistent. Manufacturer or supplier information. In most cases, we are the manufacturer. We can't get it right necessarily. Supplier information, probably better, depending on who the supplier is. And worst case scenario, you can calculate the weight, and it's going to teach us some skills to learn to use to calculate weight. Take it with a grain of salt. 2 steps to determining load weight. You can find the volume, measure the load dimensions, and use the volume equation for the load shape, and find the weight, multiply the volume by the density. So if you can find all this information, densities are pretty easily available online. Density of any given wood, density of a plastic, density of steel, density of concrete, to some extent, you can find online. Material density, this is about the only one you really need to sort of remember, and even this, the only thing I remember is that 1 square foot, 1 inch thick is 40 pounds. It's not exact based on this, but it's a good enough number that you can work with it. If you have a square foot that's a half an inch thick, it's 20 pounds. A square foot that's a quarter inch thick, 10 pounds. It's just easy to remember, and it's easy to apply to just about anything to roughly calculate the weight. And the one thing I will stress is if you are calculating weight, over-calculate. If you calculate it to be 5,000 pounds, call it 6, call it 7. It's not going to hurt you. You're never going to go wrong overestimating the weight on something. You can definitely go wrong underestimating the weight on something. Oh, it's probably only 2,000 pounds. Well, shit, it was 6. Oh, fuck. Okay, so when in doubt, you can do some calculations. Always add more. It's nothing around here. It's going to matter if you rig for an extra 1,000 pounds, and the difference in rigging is basically negligible. When in doubt, just over rig everything. That also accounts for all your damage and stuff. Hopefully you all know the standard ton or the imperial ton is 2,000 pounds, not to be confused with a metric ton or 1,000 kilograms, which is 2,204 pounds. Everything around here is in imperial. It's all it's all imperial tons, 2,000 pounds. You'll see it on all of our cranes. You'll see it on all of our rigging. It's all imperial. Weight estimations for approximate weights, you can use a boxed volume formula by determining what the smallest box the object could be enclosed in. Again, this will inherently overestimate because you're treating it as if this entire box is full of whatever this material is. Oh well, again, if that gives you 1,000 pounds more, who cares? It's not going to hurt to overrig it. Even with the round object, if you treat it like it's a square, oh well, you're going to overrig it, so be it. It does give us some creative ways to figure out the mass of any given object. The new way of doing round things is to pretend they're flat. Honestly, in my pipe fitter days, there was charts all over the place that told you how much any given pipe weighs based on a foot. A foot of this pipe is 100 pounds, a foot of this pipe is 50 pounds, and you just multiply by your length. It's probably easier to find that stuff online than to go through this. That being said, this particular example is going to show up on your test. So you might want to double or pay attention to that one. And this one's a little more straightforward. You can just pretend this thing is flat and then just multiply by your length, width, and your thickness, and your height. The pipe is a little less intuitive, but it does work. So basic ways to calculate mass is your length, width, and height times your density. So in this case, it's 3 by 2 by 5. Gives us 30 cubic feet. Find the weight using our density of steel. The other thing to make sure you're doing is make sure you are using the right density. In this case, it's cubic pounds per cubic foot. We've calculated our dimensions in cubic feet. If you figured this in inches and then you use cubic feet here, it's going to fuck it all up. Make sure you're using the same units of measure. I mean, if you've gone through trade school, you probably had to figure all this stuff out already, but it's still a good refresher. Most of our stuff here, we're not necessarily going to calculate. We have access to information. To some extent, you can kind of just tell. If you've got a 4,000 pound sling and you're lifting up this table, you're probably good. You don't need to calculate the weight of the table. It's not 4,000 pounds. Even this contraption here, this servo rack, I don't know what the hell it's made of. I don't care. If I have a 2,000 pound swing, it's going to lift it up. I mean, there is a certain level of common sense involved with this stuff. You don't have to do this every time, but being able to do this is a useful skill. Especially if you wind up somewhere where you don't have access to information, or if you've only got 1 or 2 slings to choose from. So here, this is the one example they're going to use in the book for the test. So this is taking a hollow round shape, or a pipe as it's also known, and calculating the mass of it. So we just take the diameter, that turns in, the length and thickness. So the 3.14 being pi times the thickness times the diameter times the length. gives us a volume of 5 cubic inches, or 5,000 cubic inches, sorry, times that by our density. Again, biggest thing to make sure is we're using cubic inches, and cubic inches gives us a total of 1,400 pounds. This is just doing it different using the radius, so it's the radius times the length. Again, if trigonometry and all this volume stuff isn't your thing, then you can look online and it'll remind you how to do all this stuff. The only one I think they have on the test is the round pipe one. But always make sure you're using your right cubic inches to cubic inches times by your density. Densities can be found online. There is a little chart in the book. 99% of what you're going to do around here is going to be steel. And again, the simplest thing to remember, the only thing I take away from all this is that 1 square foot, 1 inch thick, is 40 pounds. From there, you can, if it's 2 inches thick, it's 80 pounds. If it's 3 inches thick, it's 120 pounds. And then you just have to figure out your total surface area. Now, this one's going to be quite elaborate. They're going to break this creative little structure here down into 1, 2, 3, 4, 5 different parts. Again, this is a good exercise in the sense of you can do this if you do not know. After years of experience, you can kind of gauge weight by looking at things. But if you have to, you can go through these motions so you can figure out the mass of the circular thing. Then you can figure out the mass of the small round thing. Then you get the second small round thing, because this is, so this one's got a different radius. This one's 3 inches. This one's 4 inches. So you can't tell from the picture very easily with the different sizes. So you'd have to do different calculations. Then you can figure out the mass of the top part, the mass of the middle part, and the mass of the bottom part. Same thing, it's always effectively going to be length times width times thickness or height times your density. Then you can add them all together and discover that this creative little object weighs 3,332.8 pounds. Does this totally mystify anybody? Vitaly, is this totally foreign to you, or does it sort of make sense? And I'm picking on you because I know you haven't done this before. I know he's gone through trade school. I think he went through trade school, but it might have been a few years back. And I know you're going through trade school, so you've had to do a lot of math.
That would just take me quite a bit of time. I'm slow with this.
No, and math is not everybody's thing.
Yeah.
And again, the odds of you ever doing this is pretty slim, but you understand the concept,
Yeah.
right? Yeah. Vitaly, does the concept make sense to you? Okay. Again, it's useful if you're gonna, whether you do it or not, that's debatable. Now, this next section, again, this is all part of the advanced rigging course. It can get a little convoluted, especially when we start doing the unequal, non-symmetrical loads. So center of gravity, of course, is where the mass is centralized in an object. In a symmetrical object, the center of gravity is the center. Nice and easy. No harm, no foul. I can't remember if they actually ever say this, but I'll say it now. A simple way to find center on any given object that is uniform and symmetrical, if you don't have a tape measure, just measure from the ends. I mean, it's all well and good to measure the overall length, divide by 2, and find the center. But if you come in 2 feet from this end and 2 feet from this end, or you could even use your sling as the length you're coming in, if this thing's 20, call it roughly 20 feet long, use a 4-foot sling, and then put your sling at that 4 feet. Do the same on each end. You're in the middle. It's just a good sheet. If you didn't know how long this table was, and you came in an equal distance here and an equal distance here, your slings will be centered on your symmetrical object. You don't have to take the dimension, divide by 2, find the middle, mark the middle, measure from the middle. That is a whole convoluted mess that you don't need to do. Just come in equal distance from each end and find nice angles, and your thing will pick up nice and level, provided it's a symmetrical thing. So the load center of mass is the center of gravity, the point on the load at which all the weight is concentrated. What's the importance of determining the center of gravity? Well, it determines the pick points for a balanced and stable lift. So in this case, they're pointing out, like, this is how they calculate out where the center of gravity is. Again, it's all well and good if you need to do it. You can figure out that it's half the dimension from length and half the dimension from the width. So it's pretty self-explanatory. It's the central mass of the object that's located right in the middle of all directions. The thickness, the length, the width, that's where your center is going to be. Then you get into stuff like this. So this is where things start getting just a little bit complex. and a little bit confusing. I've lifted an awful lot of L-shaped pipes and I've never once calculated the length. I put 2 slings on this one because it's the heavy one, and I put 1 sling on this, and I move this sling in and out till I get the thing level. Because you do it, you lift it up, if it starts to pick up this end first, you move this back a little bit. If it starts to pick up this end first, you move it out a little bit. And you can basically dial it in through trial and error, which is going to be a heck of a lot faster than sitting down at your desk, which you probably don't have, and calculating all the stuff they're going to show us while your boss yells at you saying, what the hell are you doing? Just get that thing off the ground. But it's a valuable skill. It doesn't hurt to know how to do it, but it will get a little complex. So how do we find the center of gravity of a non-symmetrical load? Well, we break that load into simple shapes. So we've got 2 rectangles here, or squares in case they be boxes. So we figure out the mass and the density and all that of each of these. Density should be the same. So we do the same thing for A and B. So the total weight of this entire thing, so we now know that A, based on our length times width times height times density, is 11,700, and then B is 5,800. So very obviously A is a whole lot heavier than B, so you're going to want to do most of your rigging on this, and then a third one on this, and depending on where that third one is, it's going to lift up level. But if you wanted to get it perfect the first time and impress everybody, you could go through all this, and that's just fine, especially if you need to lift it up in this orientation. But now they're going to show us, so there is our central, or because these are symmetrical pieces, this is symmetrical and this is symmetrical, the center of gravity of each part is here and here. But because of that difference in weight, the center of gravity is closer to the heavy one, so it's going to be somewhere in around here. I only know that because I've seen this slide a bunch of times. So there's your line between your center of gravities, and now you're going to do a little calculation where you take the heavy end and divide it by the total weight. So you take the 11,700 divided by the 17,000 total weight, and you get 67% towards the heavy end. So 2/3 of the way down this imaginary line, which conveniently is about right there, is your actual center of mass for this object. Now they're using a ruler which looks like it's metric, doesn't really matter. It's just a visual representation of finding 60% of the way down that line. So 60% of 50 looks metric, but it's apparently imperial because it's intense. That's how imperial works. I guess whoever did this, I didn't know how to read a ruler either, is going to put you there. Again, is anybody likely to do this in the field? Probably not. Stuff like this starts to matter to me. If you work from a moot and you're lifting a bridge, you're going to want to figure out where the center of gravity is, because it's a bridge. If you're lifting a weldment and welding, you're probably just going to fuck with it until you get it right, if you don't already know. If you sit down and get your glasses on and sit there and start doing the math, Clay's going to horsewhip you until you get that thing in the air. But it is a useful talent to know that, yes, you can do this, and in theory, now the problem becomes where the heck do you attach your slings to achieve this, but now you know that your hook on your crane is probably going to want to be above that center of mass. And when knowing it's only half the battle, rigging it to achieve it is going to be tricky as well. But that's how you can go about doing it. The pick points are where the rigging is connected to the load. Again, you don't always get to pick the pick points. If you want to just choke this wherever, that might work. Maybe you have engineered lift points that you can't choose. This is all perfect situation that they go through here. Real world is going to be different. And if you're not sure, talk to someone who knows more than you do and work it out and do trial lifts. And don't lift it up above everybody or lift it off the ground until you're sure you have it right and everything's going to stay. User-selected rigging attachment points may not be suitable as pick points. Suitability must be determined by a qualified person. So in theory, you are a qualified person, but if you're only qualified if you feel qualified. If you don't feel comfortable, you're not qualified. You're not competent. You might be certified because you passed this course. You are not competent because you are not comfortable doing whatever it is they're putting in front of you to do. Lifting lugs. Lifting lugs definitely make life easy, especially on a symmetrical load. The one on the right there is nicely welded, looks fantastic. We want to make sure the orientation is correct. Make sure they are actually engineered, not makeshift. Make sure they're in good condition and they're aligned in the correct direction. This is the correct direction for this object because the slings are going to go that way. So we want that shackle to be able to move. If they were the other way, perpendicular to it, they would try to bend over, which is what it's going to show us soon. So the one on the left is correct. The shackles are allowed to bend, to roll over and pick up the way they want. In this case, these are going to side load and try to bend over, because that could happen. Again, that's because all the force is always trying to go towards the middle, and now you're side loading these things and potentially shearing them off. And while the weld is the strongest part of anything being welded, everything around the weld is weak as fuck if you don't do it right. So the heat affected zone around that weld is actually your weak point. The weld itself won't rip out, but if the lack of penetration will rip out, or it'll break off right above the weld like in this one. Tapped blind holes. So a blind hole is a hole you can't see through. Common thing around here might be, well, there's some weldments have them. Some equipment we get from vendors have them. So if you cannot see the other side, it's a blind hole. Make sure that they are perpendicular to load face, so they're actually straight up and down. Make sure there's sufficient depth for the hardware you're using, and that the threads are in good condition. And it's up to you to make sure you know what the threads are. If that means you got to get a thread pitch gauge in there or something, don't just thread in whatever you think is right. You might damage some expensive finished product, or you might get it in just enough, again, to get it off the ground, then have it fail. Tapped blind holes. Continue to integrity of the load where the eye bolt or hoist string attaches is the responsibility of the end user. You are the end user, so if you're going to use that hole to lift, you need to make sure that hole is safe to lift and that you've done your diligence and got the right thread pattern, the right size, the right engagement, all that good stuff. Untapped through holes, so this could be a hole just drilled through a piece of steel. Same thing, make sure they're perpendicular to the load and use properly sized eye bolts or hoist strings. Non-fixed pick points, again, that is terrible rigging. 2 baskets in an angle like that, just a recipe for disaster. All that force is trying to pull them together, and that's what will happen if things aren't going to go perfectly. Consider your finish and smoothness affecting your grip on the load. Edges, protrusions, and abrasive surfaces require sling protection. If the pick point is directly above the center of gravity, the load will bounce. Pretty straightforward. If multiple pick points are selected, equal distance from the center of gravity, the load will lift and balance stable. So if you've got a symmetrical load, again, and conversely, this is what I was talking about. You can be equal from the center, but if you go equal from the ends, conveniently, you're also equal from the center. And it's easier to figure out the equal from the ends, because you don't actually have to figure out where center is. So which load is stable in this case? Guesses?
Right.
Yeah. So the reason for that is the center of gravity is below the pick points. That one on the left is going to want to rock and flip over, and it can get really ugly really fast. I've seen things flip over in the air in the field. It's terrifying. Those 3-point picks where 1 point lets go. Things are slippery. Things are too much of an angle. It's pretty bad when something 30 feet long goes like this and falls to the ground. It's not something you want to see happen or be close to when it happens. And things like that are the same idea. You're just setting yourself up for disaster. Basket hitches must contain a load from the sides above the center of gravity. Crushing force, this is a huge one. Whatever you're lifting, you have to make sure it's rigid enough to handle the forces being applied. If it starts to bend, it could literally buckle, depending on what it is, spin wall pipe, sheet metal, whatever it might be, if the load's not stiff enough. The load is shared when supporting by 2 slings. The load share depends on sling position from the center of gravity. So in this case, each one's getting half the load because they're equal distance from the center. Pretty self-explanatory. When slings are connected to the same hook, the amount of tension on each sling increases. So this is something that's important. Whether you remember the exact numbers or not is debatable, but remember the massive increase that happens when you apply angles, because it should affect what slings you choose and how you're applying them. So to calculate the changes in sling tension at the various sling angles, and this is something that is on the test as well, a load angle factor must be used. So to calculate the load angle factor, we take the length of the sling, which is pretty straightforward, divided by the height. So we have the length of whatever the sling is, call it 5 feet, the height, say 4 feet, divide them, you get our load angle factor. Conveniently, they're going to use 6 and 4 feet here. So we take our length of 6 feet, divide it by our height of 4 feet, and we have a load mass of 10,000 pounds of the actual load itself. So 6 divided by 4 is 1.5. Define the sling tension per sling. And again, the sling tension is effectively the load on the sling. And this is how you can get your load to weigh more than your load weighs, which doesn't really make sense. But when you apply the physics we're about to learn, it does make sense. And it's really easy to do things wrong if you're not careful. So we take our tension, and the reason this is half is because each sling theoretically has half the load weight. So we take half the load, or half times the load weight times the load angle factor. So despite the fact that this thing only weighs 7 or 10,000 pounds total, each of these slings is carrying 7,500 pounds. So how the fuck is that? It's magic. All of a sudden this thing weighs 15,000 pounds. Well, it still weighs 10,000 pounds, but you're putting 15,000 pounds of tension on those slings. Not each one, but if you took two 5,000 pound slings, because hey, it's only 10,000, and then you did this and put these angles on here, well, you're putting 7,500 pounds of force on a 5,000 pound sling. The numbers, the basic numbers of 10,000 pound load, 2 slings, 5,000 pounds. Not once you do this and apply that load angle factor, you're actually overloading those 5,000 pound slings. So this is where this stuff starts to kind of matter, and you have to take this into consideration. Another reason why I'm a sucker for just, if I've got a 10,000 pound object, I just grab 2 10,000 pound slings, or the closest. Because then, this is relevant, kind of. I've got 2 slings capable of holding whatever angle I throw at it, and that thing is not going to be overloaded. And if those slings have a nick in them or something, I'm not going to be overloading those slings because I'm being too demanding because of the tension I'm putting on them. So another example, this one's got an 8-foot long sling with a 5-foot high between the load and the hook, total weight of 8,000 pounds. So you take your length divided by your height, gives you 1.6, not much more than 1.5, but a little bit. Then you take your half your load times the load, or half times the load times the load factor. So each of these slings is now supporting 6,400 pounds. So again, if you took that 8,000 pound load weight and figured, fuck it, I got 2 slings, I'll use 2 4,000 pound slings. Nope, not when you're doing it this way, because you're putting 6,400 pounds on each sling, which is way over the 4,000 pounds the mass alone tells you can use. So take this stuff into consideration. Again, if you use 2 8,000 pound slings, or whatever you can find that's closest, you'd be fine. So a perfect symmetrical equilateral triangle, 3 standard angles to form a 60-degree horizontal sling angle. The other thing you have to know for this, one little basic fact, a triangle has 180 degrees. If you didn't already know, don't forget the triangles have 180 degrees total, so all 3 angles in a triangle have to equal 180. That'll help for your test. In this case, this is a nice equilateral triangle. It's all 60 degrees. Every dimension is 10 feet, 10 between, 10 up. Easy way to tell this is if you lay your sling down, your sling will conveniently reach the other pick point. Now when you've got engineered pick points, you might not be able to pull this off, but it does make things nice and straightforward. But your load angle factor is only 1.155, which is only a 20% increase in tension instead of the 50% increase we saw earlier on. So that's a nice straightforward. With 60-degree angles, we can use a few different variations on hitches. That symbol there is for if we had engineered pick points. 2 vertical hitches with angles, 2 single chokers, 2 double wrap chokers, or 2 double wrap baskets. Pretty much anytime you have an angle, you cannot use a regular basket because it'll just slide toward the center. We've got to get that full wrap around it, which acts like a choke. It binds against the object. Same thing with the 2 chokers. And then this is only okay because it's implying there are lifting lugs on that piece. To verify 60-degree laydown, 1 sling on the load, like I showed you earlier, just the easy way to tell is if this from here to here is 10 feet, you laid this down, there's your other one, put your other sling there. Now you're going to have a nice equilateral triangle, which is 60 degrees all around, and you get that nice 1.155. When you start making your angles farther, because you have to go farther out, you start getting more drastic load angle factors. So in this case, you've got 90 off the hook and 245s on the unit, again, total of 180. But your load angle factor is now 1.414, so that's almost a 50% increase in your tension. So you're only good to use engineered pick points or double wrap chokers because that's going to give you 360 degree contact and really hold those slings in position on that object. This is as far as you're really allowed to take it, down to a 30-degree angle. Ideally, you would not be doing anything this drastic. I don't have my whiteboard I can draw pictures on, But if you ever had to do this in the field because you have a really, really long object, which is what I've seen, 100-foot long object, you can't just put 2 slings on it, it'll bend. What you can actually do is put a sling or 2 slings here and 2 slings here, and then those slings come back up with shackles to the main point. So you're actually using 2 slings off the hook and then 2 slings off of those, and you get a nice little mountain with another one up here. I can't draw it, not a fucking whiteboard. But it's a good way to spread the load out and avoid things like this, because the reason you want to avoid this is your load angle factor is 2. So now, if your load weighs 10,000 pounds, each sling is holding 10,000 pounds. So all of a sudden, you're putting the force of 20,000 pounds on your rigging, which it doesn't mean your crane's lifting 20,000 pounds, but your slings don't know any better, and they are just being pulled under incredible strength. And if you did the old, well, my thing's 10,000 pounds, I'll use 2 5,000-pound slings, and you did this, you are doubly overloading each sling, which would be potentially catastrophic, especially if your slings are not in good condition. So just consider that. If you start stretching your stuff out really far, it's just not going to go. It could not go well, and you definitely have to take this stuff into consideration. It's basically telling you the only way you can do this is if you have engineered lifting points, because anything else, because that force to pull in is so great, no amount of choking is going to keep those things from pulling towards the center, because you're putting so much force on it. Now we get into 2 pick points for unequal distance from the center of gravity. So again, take this with a grain of salt. This is, if you've got pick points, you're probably just going to use the pick points, and you're going to make the best of it. Hopefully you have a spreader bar, but this is going to show you how each one carries the load. It gets a little bit convoluted for the math. I don't think there's a test question on this. I can't remember. If it is, it's pretty straightforward. But in this case, 80% of the load is on the one and 20% is on the other. Because they've used simple numbers like 10 feet, it works out nice to be 80 and 20%. But obviously in real world, it's not likely to be that straightforward. And as you start to move, you can see it's just moving at 70, 60. So they're going to show us the calculation. We're going to go through this pretty quick. It's unlikely you're going to do this. Ideally, if you're ever in this position, you can either come back and reference the book or the internet, or they're going to have someone there who's an expert at this kind of stuff, or you're just going to do trial and error until you pick it up level. But you can calculate it again if you want to be the hero and make it and do it just perfect the first time. You can actually do it in theory. I'm kind of going to skip through this fairly quick because the odds of you ever doing this around here is pretty much 0. You're not going to remember it when you do it anyway. It's an awful lot of math to go through, especially ironically when they've given us engineered pick points anyway. You're just going to pick it up from those. A little more straightforward on this one because it's a box, so you can kind of see it a little better. Again, they've taken all those half dimensions. So in this case, it's going to be 50-50 because you've got a hook on at equal distance from each end, equal distance with the width. It's going to be half and half. But if you start amending this, now it's going to be 25, 25, and 50. Pretty straightforward. This one, though, in theory, it's going to be 33% for each one if they're all equal distance. And ironically, I think we recently lifted a ring like this in the assembly. Didn't we have that one unit that had that big ring around it that was part of the assembly or part of the unit? I feel like we did. I can't remember what that was for. Yeah, it was a massive
Big
ring.
cylinder that we're putting a ring around.
Yeah, it was a pretty unique unit that we've only made one of, and it had something sort of like this.
Yeah.
In this case now, the weird thing about 4 points, it's basically impossible to get anything to lift by 4 points and have it share the load. It'll always wind up being 3 points. If you've ever, dialing in a 1PT as an example I think of, you always have that one leg that's a little slack and it's really hard to get it perfect. When you're lifting up by 4 points, unless it is absolutely pristine, it'll effectively be 3 points holding, and one of them winds up being kind of a redundant backup that'll hold it if it starts to shift. So that's why it's showing us the way it does. It's not that anyone's going to carry 50 or anyone's going to carry 0. It's that it's going to shift around and be kind of kitty corner at any given time. But it'll never, it can't really fall, and it's well supported, but you're not going to be able to get everyone to hold 25% of the load. In this case, it's going to be that whole 80-20. Again, that's because, well, this is 20% and this is 80, but that's the distance. It's fairly self-explanatory, I hope, but again, all these are based on engineered pick points. Realistically, you're going to be picking this thing up with a sling and having to figure out how to hold it yourself. In this case, it's 40, 40, and 20 because we split that 80 in half with 2 pick points. So this is going to be 80, or again, this is where things start to get a little weird because again, it's going to want to hinge on 3 of them and not on 4. Same thing, more of this whole VSOL, the vertical share of the load thing. I kind of wish they didn't have this in the basic rigging. It gets a little too complex and intimidating for people. Most of you are never going to have to deal with this level of calculation in the field. If you do, stop and reference a book, read it, or contact a supervisor. You're not going to have to figure this out on your own. So here's what it was talking about. When using 4 slings, calculate the sling load based on the actual length of 2 of the diagonal slings. And that's because those are what's going to wind up taking the load. The other 2 are just going to be kind of there to hold it. It's unlikely they're ever all going to share the load exactly equally. When using larger formulas, convert the load weight to tons for easier calculations. So again, as long as you are using the same units of measure, you can do this instead of having 50,000 pounds, make it 25 tons. Is probably simpler, smaller numbers. All depends on your calculator. The main thing is you know what you're calculating for. This is starting to get right complex with the weight times the D2, the L1, H. You got multiple. This is more in depth than I'd like to have in the basic rigging course. And it's also doing it in tons just to make it simpler, so it's 5 tons instead of 10,000 pounds, just to show us that it can be made simpler. The danger zone is the area, this is something that affects us every single day. The danger zone is the area directly under a suspended load and includes any area the load can fall, swing, tip, roll, or deflect into. And that's a huge thing. It's not just a matter of a thing falling out of the sky, it's what's it going to hit when it hits the ground. What's that thing on the ground going to do when it explodes or shoots off to the side? Is it going to tip over when it hits the ground and crush someone who's 10 feet away? So the danger zone must also be considered for the area around the racking, stands, and fixtures, or where items are stored. So the danger zone for a racking is how far it's going to fall when it tips over. Crane operators and everyone associated with the lift must constantly reassess where they are standing in relation to the load to ensure they are never in the danger zone. The simplest one to watch out for is crush points. If you're floating something across the shop, don't get between the object and the wall. Pretty self-explanatory. Don't put your fingers between that object and whatever you're butting it up to. Again, it seems straightforward, but an awful lot of people have lost their fingers because of mistakes like that. The simplest one, I'll remind everyone, especially for this course and the test, don't grab things, touch things. The basic rule of thumb is you use an open palm for manipulating objects. You just guide it with your open hand. Avoid yours to grab things like this. If it weighs 50,000 pounds, grabbing it's not going to do any good. And odds are your hand's not going to do any good either. But just try to get in the habit of pushing things with an open palm and avoid the urge to grab them, because grabbing them is how you lose your fingers when it butts into something. The infamous way in the field is pipe. People put their hands in the end of a pipe, butt the pipe up to another pipe, and they lose their fingers. It's easy to lose focus, and it's easy to lose limbs if you're not careful. So yeah, try to avoid doing anything with closed hands and grabbing things, and just manipulate them with your open hand. What is the danger zone affected by? The height of the load. So if you lift it higher up, it has more stored energy. It's going to bounce farther, deflect farther. When it hits that other thing, it's going to blow that thing open wider. Dynamic movement of the load, the shape of the load, the rigging configuration that you're using, one sling versus multiple slings, for example. Deflections off equipment on the floor, so whether it hits something and bounces off of it, or whether it hits something and shoots that thing across the floor. We've had that happen. We had a failure during a test in assembly a few years back where the test itself failed to hit the ground and shot something on the ground out to the side, which could have hit someone if someone had been there. So those are all things you got to consider. And the load composition, is it a basket full of parts that are going to blow apart and go everywhere? Are there going to be projectiles coming out of it when it hits the ground, or if it breaks open, or what have you? The danger zone should be cordoned off to prevent unauthorized entry. This can be accomplished by fixed barriers, barrier tape, and signage. If you're doing something, I mean, erecting a mast is a good example. We should flag off the area. If it was to tip over, it could fall. If it's 20 feet high, it's going to fall 20 feet, and then it's going to hit something that could shoot out another 20 feet. We should be considering that and riveting off the whole area, especially when the whole operation only takes 20 minutes or half an hour. It's not a 3-day thing. It's a fairly short thing. We can flag it off and exclude people temporarily. Working with any part of your body in the danger zone is accepting an unnecessary risk. So even if that's just your toes underneath the thing you're lifting, well, if that thing falls, it's going to take your toes with it. Never reach under a suspended load. Never tie a tagline to a suspended load. Tagline should be affixed to the object before the object gets lifted up, not after it's lifted up. Never readjust a suspended load, and don't do any assembly work with a suspended load unless a hazard assessment has been completed and reviewed by all affected workers. In this case, just don't. I think it's trying to show us you wouldn't want to walk underneath that crate that's coming sideways off that truck. Obviously, don't stand under a suspended load, whether that's your foot or your whole body. Don't lift over other people. If there's other people in the area, tell them, warn them. Horns are temperamental. Most people will just ignore horns anyway when you honk them. So just talk to your coworkers. If you're lifting something up, say, hey bud, I'm going to lift this. I'm going to put it over there. They'll say, okay. And at least when they stand up, they won't be scared because this thing has come near them, or you've done this, lifted this object and haven't warned them. Just look out for each other, communicate.
Isn't the danger zone how they read that thing?
Yeah, I don't really like that. It's not so. I think it's not
like
so
they
bad.
piled it. No, well, it looked like they piled it all onto the hook.
Oh, that's fucked. Yeah. It seems like they have almost 4 ends to a sling in that one little tiny hook, and it looks like it's a chain fall to boot. So I don't like that at all. You're right. It's wrapped up. It's twisted. Like that just looks like pretty shitty rigging. Whether it's super heavy or not is debatable. Although those look like pretty thick slings given the size of them compared to the truck. But yeah, it doesn't look like the best example. And there's no person or even fake person there to show. So I've never quite figured out the point of this slide. But don't walk under stuff. It's floating.
That's right.
Crush points are where fingers, hands, feet, or other body parts can become crushed or resulting in bruises, cuts, broken bones, and death. And it's true. I mean, if you're lifting something heavy enough, it doesn't take very much for it to crush you. It's a 50,000-pound object. It doesn't take very much movement to crush you between a wall and the object and crush every rib in your body. And you'll probably look fine, but you will not be fine, and you will not win. I've seen lots of people reach out and try to stop a 20,000-pound thing that's moving this slowly. You can't. You just do not have the mass to stop something that heavy. It's super hard, so don't even bother trying. But it's human nature. Put your hand out and stop it. Yeah, you're not Superman. You're not stopping that thing. It's going to just keep coming and take you with it. Crush points can occur between the load and the rigging, between the rigging and the crane hook, between the load and equipment, during lifting, load travel, final positioning, and setting the load down. Just an example of in this point, in this case, the wall example. So you wouldn't want to be walking along between that object and the wall. A tagline is a rope of suitable strength, construction, and length attached to a load to control location. We don't often find cause to use taglines around here, but that being said, we probably should more. If we're lifting a unit up and transporting it from one end of building 2 to the other end, we should probably be using a tagline. Again, it's really hard to stop big objects with your hand. Having a tagline to pull on is a pretty good way to do it, and you're going to have to work with the object. If it's swinging, you're going to have to pull on it every time it swings away from you to slowly take the swing out, because you will not just be able to stop it dead in its tracks by holding the tagline. It's just going to drag you across the floor, but you can slow it down. They should be good rope, nice nylon rope, not that shitty stuff you buy at Cane Tire that has all the bits sticking out. It'll rip your hands up if you use it, that yellow stuff or whatever. You want it to be nice, soft rope. I know Shane bought a roll of it years ago that in theory still floating around. It's like 1-inch rope.
Well, we actually use taglines quite a bit.
Do you actually?
We do.
I'm happy to hear that. I know we didn't used to. I
Like
had to yell at people, but
when we move manipulators and stuff around or anything, real big equipment.
Good. No, and I'm happy to hear that. I know for the longest time they weren't very common, and I used to have to yell at Neil. Neil was a poor example, but he'd be transporting any random unit across the whole shop. And he's trying to run a crane and run the object. Like, dude, put a tagline on it and get a second person.
A lot of people just hold it
Yeah.
instead of tagline. They'll physically
they'll physically
Grab.
hold the object. It
Yeah.
usually means your feet are basically underneath it on a good day.
Yeah.
And it's so much more awkward. Going down the rabbit hole here, and I'm sure we'll get into it, but one thing that we have sucked at in the past, and maybe we're getting better at, is a lot of lifts should be at least 2 people. You really shouldn't have the crane operator running the tagline and running the crane. If you're going to have a tagline, have a second person. We don't need to have 4 people per lift, a signal person, an operator, 2 taglines. We're not outside, it's not windy, our shit's not spinning around in the wind outside, the crane itself isn't swinging. I mean, an RT crane, when it swings around, it imparts a swing on the load, so taglines are helpful. Plus, you have to maintain the load and orientation while the crane swings. We don't have any of that problem, but 1 tagline and 1 operator is probably enough for most lifts. And unfortunately, in a lot of cases, we're doing everything ourselves because we are either welding it in our own bay, putting it where we want it, or we're installing a motor in the back of a fucking positioner, and we basically have to do both ourselves. It's a blessing and a curse because you're the one whose hand's in danger and you're the one in control, so that can be comforting, but it can also be bad because if you get caught in a pinch point and your body tenses up, now you're pressing that button harder and it's just going further and it's making things worse. So it's a fine line. Sometimes the space available, the people available, it's not indicative of how many people you should have. All I can stress as the safety guy is if you think you need another person, get another person. I don't see Allie or Jacob or maybe Dallas yelling at you if you're having too many people involved in a lift. If you need another person, even Lance, you're not Lance. If you need Lance, grab Lance. I mean, you guys are all a team. In the unlikely event you're doing something awkward, grab Jeff, he's right beside you. Get that second set of hands for 2 minutes. No harm, no foul. Don't do it yourself because you think you have to or because you've done it 1,000 times. If it's awkward and you can't properly control the object and the crane, take the extra minute, get a second person. It's worth it, and it saves the hassle, and it saves potential damage to things, never mind your own well-being. So that's my speech on that. But I know we often struggle around here. We find ourselves doing a lot of jobs by ourselves, and we do it that way because that's kind of how it's been expected. That doesn't always make it the right way to do it. So I'm happy to hear that teamwork is still going and people are asking for help. What items should not be used as tagline? Oddly enough, I thought they go into a list here, but they didn't. Don't use electric cords, don't use other slings, don't use random objects as taglines. Use a proper piece of rope. In a perfect world, it would have a nice hook on it so you could latch it to stuff. Don't just use whatever object is around, like that extension cord in the corner or something. I'm not exactly sure what's wrong with that one. Crane operator must have only 1 task. So again, so he's operating the crane and he's running the tagline. It isn't ideal. In most cases, if you have to use a tagline, you should have 2 people. The tagline's too short, the operator's standing in the danger zone. That's hard to say from this perspective. It looks to me like it's long enough, but I guess it depends where it's going. Of course, the other operative thing is you can't push a rope, so make sure your tagline's in the right place so you're pulling on it and not trying to push it. Taglines are used to keep the load from rotating, rotate the load as needed during travel and at the destination, provide separation from the load, and avoid touching the load which could pose a hazard. Taglines not to use or should not be used to pull a load out of its natural suspended position. If you're using taglines, use the crane to move the load. Don't tug it into position with the tagline. Don't fight the crane. Not to balance the load, not to support the load, and to hold the load against the wind forces. Well, ironically, I don't know how you don't use a tagline that's loaded against wind forces, but whatever. I guess if it's too windy, you shouldn't be lifting anyway. RT cranes are only useful in certain wind conditions. After that, you can't use them regardless. Non-conductive rope, such as nylon or polyester, sufficient diameter to hold it firmly to reduce the risk of slipping out of your hands or getting rope burns. Sufficient length for separation from load at all heights. And no loops, hooks, or knots that could be caught. Don't tie the tagline around your body. Attach the clothes end for ease of load control. Attach the corners of loads that require 2 or more taglines. Attach it to a lug, bolt holder, wrap around the load with a secure knot such as a bowline. Do not attach tagline to rigging supporting the load. That's because you don't want to tie a tagline to a shackle. The shackle is already being used to hold the load. You don't want to add the strain of pulling on that tagline to the shackle. You might break the shackle, which in turn could drop the load. Might be unlikely, but it's not what you want to do. tie the tagline to somewhere else on the load that isn't already part of the lift. Planning is required to identify the number of taglines and tagline handlers required to ensure they can work safely around one another and the load and instructions. Attach the tagline while the load is on the floor. Don't wrap the tagline around your hand, arms, or body, and never reach under a suspended load to retrieve the tagline. Use a tagline retriever. Much like a ball retriever in golf, I guess there's tagline retrievers too. Never seen one. Can't imagine asking for one. But if it's a thing you're doing enough, it might be something you could look into. The biggest one there is don't tie taglines around yourself. Don't wrap the excess around your waist or tie it around your arm. When if that thing fucks off, you're either going with it or that body part's going with it. I've seen a lot of guys wrap it around their arms and then get pulled across the yard. What I would usually do is hold the tagline in one hand and then hold if there's excess, make a nice loop and hold it in your other hand. So if anything does happen unexpectedly, you can drop them both. There's a little bit of a time delay. If you just wrap the excess around your arm, I guess you don't want your arm very much. Like I say, stopping something that weighs 10 tons with your body mass is not going to be enough. Establish clear communication with the crane operator and other tagline handlers. Stay away from the load, clear, float, swing, and potential crush points. Tagline should not be used if it creates a hazard. Yeah, don't use one if it's going to make things worse. Keep the tagline as close to horizontal as possible to maximize effectiveness, because if the tagline is going from you straight up, you're not pulling on anything. All you're going to do is pull the load down, and you're not going to be able to handle it. You want to be, the more horizontal that line can be. If the object was in the lunchroom, I could pull it. If the object was straight above me, not only is it dangerous, I can't do fuck all. I can't really steer it. You're going to get a lot more, it's just the laws of leverage. It's going to work a lot better the more horizontal it is. So make sure you have the right size one for what you're doing. Here's a pretty straightforward example. Person tailing it has the ability to control it left and right. If you were in front of it, you can't push it, so it's not going to do any good. And if you were doing something, you could always have two people like this. Again, it all depends on how much space you have and if you have a need for it. Obviously, in this case, the person at the front is not going to have much luck because they're going to constantly try to stay ahead of it, and they can't push their rope, so good luck to them. Signals are something we don't use here very often because usually we're the one doing the lift ourselves. It's also not necessary because you can zig your partner up. In the field or elsewhere, you might find signals are very useful. I've used them an awful lot in my previous life. But around here you don't find cause. I find I signal forklift operators more than I ever signal a crane operator around here because the guy sitting in the cab can't always hear you and you're trying to tell him what to do with his load. So you end up using the same symbols, up, down, whatever, but not so much for cranes. That being said, if you are doing a lift that involves signals, make sure your signals are really clear. Don't sit there doing this. You're not balancing a basketball. Do this. Make it nice and clear and obvious what you're trying to show the person. If you're in a shop that has overhead cranes that have operators driving them, that guy's 30 feet above you and far away. You need to make obvious signals to what you want done. But I mean, if you're controlling it yourself, there's no need for any of this shit. Signaler is required when a crane operator does not have a clear view. So in the unlikely event, you need to put something somewhere where the crane operator can't see it, you're going to have to use a signaler. That being said, if the operator can't see what's happening, you kind of have to take into account the fact there's going to be a delay from when you see what needs to happen to by the time your body starts doing what needs to happen, to him interpreting what needs to happen, and him actually affecting what needs to happen. So you kind of got to consider that if you want him to stop before it needs to stop, if that makes sense, because it's got to translate to the person pushing the button or taking the finger off the button. But again, we're moving really slow. Most of this is pretty straightforward, and again, the odds of using signal people in the shop around here are pretty slim. A signaler must be competent and designated by the employer for the lift. Again, all of you will be competent when you're done with this course, you'll be trained, you may not be competent. Training is easy, competency comes with experience, and anyone can stop a lift. The stop signal must be obeyed no matter who gives it. Signaler must be in a safe position for the duration of the lift. Obviously, if the signalman has to keep dancing out of the way of the load, they're not in a very good spot. Signaler should face the operator and ensure the signals are clear. Maintain that eye contact thing. Crane operator should not respond to unclear signals. If you don't know what the heck your partner is trying to tell you to do, don't do anything. Nothing should go wrong if you don't move, but if you interpret it wrong, you can crush someone's hand or what have you. So for basic hand signals, hoist or up, as the case may be, is just It's just like this, point up, rotate your hand, and it says small. I would make it more dramatic so they can see you. Down is the opposite. And again, if you ever find yourself in the field, big dramatic ones are a lot better because that guy's probably 80 feet away from you, sitting in a cab listening to music. He can't hear what you're saying. If you're all he's going to be able to tell is what you're doing with your hands. For bridge travel, you want to push your palm in the direction that you want the bridge to go. Trolley travel, use your hitchhiker finger and point in the direction you want the travel to go. A stop is just your arm extended with your palm down. An emergency stop is raising your arm with the palm down. Again, anybody can give that stop. I always imagine Jacob coming out of the hallway by his office and signaling to someone to stop because he's seen something that you don't see maybe. Again, we don't have 2 trolleys, so we don't have to worry about this stuff, but it is a thing. If you find yourself in a place that has multiple cranes on one rail, multiple trolleys, get to know whatever it is they want. There'll be variations on a theme, just like if you go somewhere that has remote controlled crane operators, some of them do. If you want them to move slowly, you use your hand like a brake, so this is up slow. Same thing, down slow, but your hand is the brake, slowing it down. Another one that was used in the field commonly was this, the penguin hand. This is up slow and this is down slow. But this symbol, if it's accepted, is only good if the operator can see you doing it. If you're standing like this, you can't see what I'm doing. So you got to make it big and obvious. This is helpful if you're holding the tag line and trying to give signals. I'm going to tell you, because you don't have 2 hands to do this. So you use this hand and you do that motion. It's one of the few ones I remember from the field that was unique. And it's helpful because often you weren't holding the tag line. Conveniently, that's it. Do you guys have any questions or concerns on this? Half of you have probably already done the damn test, and that's totally fair too. All good? Perfect. So I just need you to write your name on the sheet I'm going to give you. Clark, I still get your name wrong. Damn it.
C.
Oh shit, and I know that too. I transposed it wrong. I know it's SCH. So yeah, put your name on this guy in the top left corner there, and then you can go ahead and fill it out if you haven't already filled out the answers to the test in the back. I actually left them in there on purpose this time, thinking, well, someone will get ahead again. It's 11:30, so yeah, after the test is done, you're free to go for today. We'll recongregate tomorrow, and then we'll have our test tomorrow after our practical test tomorrow afternoon.